Transforming raw cane into crystal clear sugar takes extreme heat and unstoppable industrial power on a scale you have never seen before. Inside these giant factories, thousands of tons of raw material are pulverized and dried with precision to produce the sweet white crystals used everywhere you look. In this documentary, we take you inside the stunning world of sugar production. Stick around to witness an unbelievable process in the making. Industrial sugar production begins with harvesting, and depending on the region and facility specialization, the factory will receive either sugarcane or sugar beets. These two crops require distinct processes to extract sucrose, though many of the underlying steps, washing, crushing, juice clarification, and concentration, are similar in principle but differ in machinery, timing, and chemical inputs. Let's start with sugarcane. Sugarcane is a tall, fibrous grass grown in warm, tropical climates. It is harvested either manually, using machetes, or mechanically using harvesters that cut the stalks and strip the leaves in a single pass. Once cut, the cane begins degrading immediately, so it must be delivered to the processing facility quickly, typically within 24 to 48 hours, to preserve sucrose content and prevent microbial activity that would convert sugar into acids. The cane arrives at the factory by truck and is offloaded into massive intake yards. These yards are equipped with cranes or grab loaders that lift entire truckloads of cane and dump them onto conveyors that feed the primary cleaning line. Before any juice can be extracted, the cane must be washed to remove soil, leaves, and insects. This is accomplished with a combination of rotating drum washers and high-pressure spray systems that bathe the stalks in recycled processed water. The water itself is filtered and reused in a closed-loop system to reduce environmental impact. Once clean, the cane is conveyed to a chopper station. Here, high-speed rotating blades slice the cane into short sections to expose the inner fibrous material. The chopped cane then moves through a shredder, a powerful hammer mill type machine that tears the cane into finer particles. This dramatically increases the surface area of the plant material, making the sugar easier to extract in the next stage, milling. The shredded cane is now ready for juice extraction via mechanical milling. This takes place in a series of large, heavy-duty roller mills, typically arranged in a tandem line of 5 to 7 stations. Each station consists of 3 rollers, 2 lower and 1 upper, that compress the cane with immense pressure. As the cane passes through each station, more juice is squeezed out. Water is sometimes sprayed onto the crushed cane, a process called imbibition, to help wash out more sucrose during the final passes. The resulting juice, known as mixed juice, is a cloudy, pale green liquid that contains not just sucrose, but also fibers, proteins, organic acids, and soil particles. What remains of the cane after this process is a dry, fibrous residue known as bagasse. Rather than being discarded, bagasse is transported to a boiler house where it is burned as fuel to generate steam and electricity for the plant itself, often making the facility energy self-sufficient. Meanwhile, the mixed juice moves to the clarification phase. Before sucrose can be crystallized, impurities need to be removed. The first step is heating. The juice is pumped through a series of shell and tube heat exchangers to bring it up to around 105 degrees Celsius. This temperature helps precipitate some of the colloidal particles and also prepares the juice for chemical treatment. In the next stage, the juice is sent to a reaction tank where lime, typically calcium hydroxide, is added. This raises the pH of the juice and helps neutralize acids, precipitate proteins, and coagulate other impurities. The exact dosage of lime is tightly controlled using inline pH meters and flow-regulated injection systems. Flocculants may also be added at this stage to help bind the fine particles into larger clumps. After chemical treatment, the juice enters a clarifier, a large settling tank where gravity separates the solids from the liquid. The solids, known as mud, settle to the bottom and are periodically removed through rotary scrapers and pumped to a filter press, where the water content is removed. The resulting cake is either composted or used as a soil amendment. The clarified juice, now a light amber color and much cleaner, is drawn off from the top of the clarifier and sent to the next phase, evaporation. Let's now consider the sugar beet process, which starts quite differently. Sugar beets are harvested using machines that dig them from the soil and remove most of the leaves and dirt. At the factory, the beets are washed in flumes, long channels of water that carry the beets through a series of mechanical washers and screens. Stones and heavy debris are removed using density separation, while fine silt is filtered out with mesh drums and hydrocyclones. Once clean, the beets are sliced into thin strips called cossettes. These are fed into a diffuser, a long vertical or horizontal tank where hot water is sprayed over the beet slices. The water temperature is controlled to around 70 degrees Celsius and flows countercurrent to the beet material, maximizing sugar extraction. The sugar diffuses from the plant cells into the water, forming raw beet juice. This juice is then pumped to its own clarification stage, where lime and carbon dioxide are used in a process called carbonation. Calcium carbonate forms during the reaction and binds impurities, which are then filtered out, leaving behind a clarified beet juice ready for concentration. Both the cane and beet clarification processes converge at this point. They now have a clean, thin juice rich in dissolved sucrose. The next step in both methods is evaporation, which we'll explore in full detail in the following section. But for now, we've completed the complex, high-volume, highly monitored beginning of sugar manufacturing, where plant material is transformed, filtered, and chemically prepared for crystallization. Every moment of this phase is controlled with real-time feedback systems, mechanical separation equipment, and chemical treatments that must be perfectly balanced to set the stage for pure, white sugar to eventually take form. With the clarified juice now prepared, whether from sugarcane or sugar beets, the next major operation in industrial sugar production begins: evaporation. This process is designed to concentrate the diluted juice, which at this stage contains roughly 12 to 16% sucrose by weight, into a thick syrup known as thick juice or syrup, with a sucrose content of about 60 to 70%. The transition from thin juice to syrup is achieved by removing most of the water through a carefully staged thermal process. This concentration step is not just about volume reduction, it also creates the right conditions for crystallization to occur later with control and precision. Evaporation in a sugar factory is typically carried out using a multi-effect evaporator system. These systems are composed of 5 to 6 large vertical vessels, known as effects, connected in series. Each effect operates at a slightly lower pressure than the one before it, allowing the juice to boil at progressively lower temperatures. This setup significantly improves energy efficiency. Steam generated in one effect is reused to heat the next, conserving thermal energy throughout the process. The clarified juice enters the first effect and is heated with steam to just above its boiling point, typically around 115 degrees Celsius. As the juice boils, water vapor is released and rises to the top of the vessel, while the increasingly concentrated juice remains below. The steam from this first vessel is then routed into the heating coils of the second effect, where it causes the juice in that chamber to boil at a slightly lower temperature due to its reduced pressure. This cascading effect continues through all stages, progressively concentrating the juice without requiring additional high-pressure steam inputs at each stage. Throughout this process, automated sensors track the Brix value, sugar concentration, temperature, and pressure in each vessel. Flow controllers and level sensors regulate how much juice is transferred from one effect to the next, ensuring consistent residence time and thermal exposure. Operators monitor these values from a centralized control panel equipped with real-time displays and alarms. If any chamber's temperature deviates beyond acceptable limits, the system automatically adjusts steam input or juice flow to compensate. By the time the juice exits the final effect, it has thickened into a dense, amber-colored syrup with a viscosity similar to honey. It now contains upwards of 65% sucrose and has a reduced water activity, which helps to stabilize it against microbial spoilage. At this point, it's ready to enter the crystallization phase, a controlled process designed to coax sucrose molecules out of solution and into solid form. Crystallization begins in large, jacketed vacuum pans. These are vertical, cylindrical vessels where the thick syrup is further boiled under vacuum to lower the boiling point and prevent caramelization or degradation of the sugar. Reducing pressure allows boiling at temperatures around 60 to 70 degrees Celsius, preserving product quality. Inside each pan, agitators or stirrers keep the syrup moving, while high surface area heating coils provide uniform thermal input. The process begins with the introduction of a small amount of fine sugar crystals, called seed crystals or slurry. These seeds serve as nucleation sites around which sucrose molecules begin to gather and grow. The timing and uniformity of seeding are crucial. If seeded too early, too many crystals form, resulting in fine-grained sugar. If done too late, oversized or irregular crystals can result, affecting yield and downstream processing. Once seeded, the vacuum pan is held at a steady boil, and the syrup is gradually fed into the vessel in a process known as strike feeding. As more syrup enters, the crystals continue to grow while the water content is simultaneously reduced by evaporation. Operators closely watch the strike through sight glasses or by withdrawing small samples to examine crystal size and consistency under polarized light. When the desired crystal size and saturation level are reached, the strike is dropped, transferred to a large horizontal vessel called a crystallizer. Here, the mass, now called massacute, is gently stirred and cooled over several hours to allow further crystal growth and uniformity. The goal is to achieve maximum recovery of sucrose in solid form, leaving behind a thick mother liquor known as molasses. Once cooled and matured, the massacute is ready for centrifugal separation. Industrial sugar centrifuges are large, high-speed machines with perforated baskets that spin at up to 1,200 revolutions per minute. When the massacute is loaded into the centrifuge, the force of spinning flings the liquid molasses through the perforations, while the denser sugar crystals remain behind. Water or steam is sprayed onto the sugar during spinning to remove any residual molasses and improve crystal brightness. After spinning, the raw sugar is discharged from the centrifuge as damp, tan-colored granules. If the plant's end product is raw sugar, for example, in a raw cane sugar mill, this product is conveyed to dryers and then bagged or bulk loaded for transport to a separate refinery. However, in a full refining operation or beet sugar plant, further purification steps are carried out to produce white, food-grade refined sugar. The raw sugar is sent to a melter where it is dissolved in hot water to form a clear sugar liquor. This liquor undergoes multiple filtration steps, including activated carbon treatment and phosphatation or carbonatation, depending on the process. These methods remove colorants, organic compounds, and trace minerals. In the case of carbonatation, lime and carbon dioxide are added to form calcium carbonate, which binds impurities and is filtered out. After decolorization and final filtration, the sugar liquor is sent through a second crystallization stage, nearly identical to the one used for raw sugar, but this time targeting higher purity and clarity. The white sugar crystals formed in this process are sharper, brighter, and finer than raw sugar, and are typically centrifuged, washed, and dried in a fluidized bed dryer. This dryer suspends the crystals on a bed of warm air that circulates through the granules, gently removing moisture without breaking the crystals. The final product is pure, white granulated sugar with a typical purity of 99.9% sucrose. It is cooled to ambient temperature and stored in silos constructed of stainless steel or food-grade plastic, protected from moisture and pests. These silos are equipped with temperature and humidity sensors, along with vibrating floors or fluidizing systems to prevent caking or compaction during long-term storage. From here, sugar can be packed into a wide variety of formats: retail-sized paper bags, industrial bulk sacks, or even liquid sugar totes, depending on customer requirements. All packaging is done in cleanroom-grade conditions, using automated lines that fill, weigh, seal, and label each unit with production codes and batch tracking information. So far, we've followed the process from raw juice to pure sugar, navigating evaporation, crystallization, centrifugation, and drying. The next segment will explore how factories handle byproducts like molasses, manage energy usage with bagasse or beet pulp, and maintain food safety, quality assurance, and environmental compliance throughout continuous 24/7 operation. Now that the core crystallization and drying stages of sugar manufacturing have produced refined, food-grade white sugar, the final phases of the industrial process turn to three key pillars: byproduct management, energy and sustainability practices, and rigorous quality control systems that ensure every grain of sugar meets the specifications for purity, safety, and consistency. Modern sugar factories are not only high-output food production plants, they are also vertically integrated resource management systems designed to handle waste, generate energy, and produce multiple co-products with commercial value. Let's begin with molasses. After the centrifugation stage, once sugar crystals have been separated from the remaining syrup, what's left behind is a dense, dark, viscous liquid, molasses. This mother liquor still contains residual sucrose along with glucose, fructose, organic acids, minerals, and other non-crystallizable solids. The amount and composition of molasses can vary based on the raw material, cane or beet, the efficiency of crystallization, and the desired yield of refined sugar. In cane sugar operations, molasses is often drawn off after the second or third crystallization strike. Rather than being discarded, it's routed to molasses storage tanks, where it is either sold as a feedstock for ethanol distilleries or used as livestock feed due to its high energy and nutrient content. In some facilities, molasses is further processed to extract minor quantities of sugar through high-efficiency ion exchange or chromatographic separation. But this is only economically viable at large scale, or where sugar recovery is subsidized. In beet sugar production, molasses has a different profile, slightly lower in fermentable sugars, but rich in betaine and other organic compounds. It is also collected in holding tanks and transported in heated tanker trucks to fermentation plants, where it can be used in the production of yeast, citric acid, or industrial ethanol. In all cases, the molasses is handled under strict hygienic conditions to prevent spoilage or microbial contamination. Another major byproduct of sugar processing is bagasse, the fibrous, woody material left over from crushing sugarcane stalks. Rather than treating it as waste, factories utilize bagasse as a biofuel. It is burned in high-pressure boilers to generate steam, which is then used to power turbines that produce electricity for the entire sugar mill. Many sugar plants operate as self-sufficient cogeneration facilities, producing not only enough power for internal use, but also exporting surplus energy to nearby grids. Bagasse combustion systems are outfitted with flue gas scrubbers, electrostatic precipitators, and ash management systems to minimize air emissions and collect residual ash. This ash, in turn, may be used in agriculture as a soil amendment due to its mineral content, or it may be mixed with other waste materials to create compressed fuel briquettes. Some advanced mills pelletize dried bagasse for sale to industrial burners or biomass energy producers. Beet processing also generates fibrous residues, known as pulp. After the sugar has been extracted in diffusers, the beet pulp is pressed to remove excess moisture and then sent to drying systems, usually rotary drum dryers or flash dryers. The resulting dried beet pulp is then either pelleted or ground into flakes and sold as animal feed, particularly for cattle. High in fiber and moderately sweet, beet pulp is valued in the livestock industry for both energy and palatability. In both beet and cane facilities, the wastewater generated during washing, evaporation, and cleaning operations must be treated before discharge. Factories operate full-scale wastewater treatment plants that include sedimentation tanks, anaerobic and aerobic digesters, pH correction units, and sometimes membrane filtration. These systems are monitored continuously using turbidity sensors, chemical oxygen demand (COD) analyzers, and automated flow controllers. In some operations, treated effluent is reused internally for irrigation, ash quenching, or process water, further reducing the factory's environmental footprint. Solid waste is minimized through integrated process design. Soil and rocks from beet or cane washing are separated and sent to land reclamation or construction material applications. Boiler ash, as mentioned earlier, is either reused or compacted and safely landfilled. Filter cake from juice clarification, rich in organic matter and lime, is collected and sold as fertilizer, particularly in regions where soil pH management is important for crop health. Alongside waste handling and energy management, quality control is one of the most sophisticated systems operating inside a sugar plant. From raw material to final product, multiple checkpoints are established to measure, record, and verify key parameters. Quality assurance starts with raw material sampling. Upon arrival, cane or beets are tested for sucrose content, fiber, moisture, and purity. These values inform process adjustments and predict yield per ton of raw input. In the evaporation stage, bricks, soluble solids content, is measured at every effect using inline refractometers. These instruments use light refraction to instantly calculate sugar concentration in real time. Operators can adjust feed rates, heating input, or flow pressure based on these readings to maintain target consistency. During crystallization, samples are withdrawn at set intervals and examined under microscopes for crystal shape, size distribution, and purity. Technicians monitor the color using ICUMSA, International Commission for Uniform Methods of Sugar Analysis, standards, with high purity white sugar scoring under 45 ICUMSA units. If color values trend too high, indicating the presence of residual molasses, operators can make real-time adjustments to seeding rates or massacute concentration. After drying and cooling, sugar samples are run through particle size analyzers and moisture content meters. The particle size must fall within strict specifications depending on the final use. Granulated table sugar, for instance, has tighter specs than coarse industrial sugar destined for beverages or confections. Moisture content is typically targeted below 0.05% to ensure long shelf life and prevent clumping. Final color, purity, and turbidity tests are logged digitally and associated with specific batch codes for traceability. Packaged sugar is subjected to additional inspection. Bags, sacks, or containers are weighed using high-speed check weighers that verify fill accuracy to within plus or minus 0.2% of the labeled net weight. Vision systems inspect print clarity, barcode legibility, and seam integrity. Packages that fail any of these checks are diverted and manually reviewed. Silos storing finished sugar are equipped with real-time inventory monitoring systems using load cells and level sensors. Temperature and humidity are also monitored to prevent caking or condensation. In some regions, silos are also flushed with dry, filtered air to reduce microbial risk in high humidity climates. Across the plant, digital SCADA systems pull data from all production stages. Operators view real-time dashboards showing flow rates, temperature curves, impurity removal efficiency, and steam usage. These systems not only ensure daily operational control, but also provide long-term analytics for performance improvement. Advanced factories even deploy machine learning tools that analyze historical data to predict maintenance needs or recommend minor adjustments to maximize recovery rate and minimize energy consumption. To comply with food safety and export standards, many sugar factories operate under ISO 22000, FSSC 22000, or BRCGS certifications. This requires documented hazard analyses, allergen control programs, cleaning protocols, and traceability audits. Every production lot is labeled with a batch ID that connects back to a full production record: raw input, processing conditions, lab results, and packaging date. Customer-specific requirements are also programmed into the system. For example, pharmaceutical-grade sugar used in oral medications must meet even higher purity and microbial specifications, and may be filtered again through fine mesh screens and sterilized using UV or ozone treatments before final packaging. In some cases, sugar is converted into liquid form, known as liquid sucrose or invert sugar, by dissolving granulated sugar in heated, purified water and, in the case of invert, breaking down sucrose into glucose and fructose using acid or enzymatic hydrolysis. These liquid sugars are pumped into sterile tankers or IBCs, intermediate bulk containers, and shipped under temperature-controlled conditions to manufacturers in the beverage, dairy, or baked goods industries. Even at this late stage, the role of the sugar factory is far from static. Engineers continue monitoring consumption trends, regulatory shifts on added sugars, and regional demand to adjust capacity and format offerings. New packaging materials, biodegradable options, and energy recovery systems are constantly being evaluated and trialed, keeping the entire facility in a state of adaptive optimization. With refined sugar now stored in silos, bulk bins, or sterile containers, depending on its intended form, the focus turns to distribution, packaging, and how this versatile ingredient is tailored to the requirements of a wide array of customers, from retail consumers to massive industrial clients. This final stage is no less complex than the upstream processing phases. In fact, it involves its own dedicated systems for handling, labeling, traceability, and product customization. At this point in the factory, packaging lines diverge into three main pathways: consumer packaging, industrial bulk packaging, and liquid sugar dispatch. Each line is specifically engineered for its product format, and all are equipped with high-speed automation and real-time quality assurance systems. For retail products, such as granulated white sugar sold in 1 kilogram or 2-pound paper bags, the packaging line begins by feeding dry sugar through a vibratory chute into a vertical form-fill seal machine. The sugar passes through a flow meter and enters a funnel that drops it into a pre-formed bag made from food-grade paper or composite film. These bags are formed, filled, and sealed in one continuous motion. The machine prints batch numbers, expiration dates, and sometimes QR codes or traceability data on each bag. Each filled package passes through a metal detector and X-ray scanner to ensure that no foreign objects are present. Then, check weighers confirm that the net content is accurate within a narrow margin. Any under or overweight packages are automatically rejected and flagged for operator review. The approved bags are collected into bundles, often shrink-wrapped into 10 packs, and sent to palletizers that stack them for warehouse distribution. For industrial customers, packaging formats differ significantly. Sugar may be packed into 25 kilogram woven polypropylene bags, 50 kilogram sacks, or even 1 ton bulk bags called FIBCs, flexible intermediate bulk containers. These bags are filled using gravity-fed hoppers mounted on load cells that ensure weight accuracy. The industrial production of condensed milk begins with the careful reception and preparation of raw cow's milk, a phase that determines the quality, efficiency, and final yield of the entire operation. As raw milk arrives at the condensed milk manufacturing facility, typically transported in insulated stainless steel tankers from contracted dairy farms, the first priority is immediate and rigorous quality assessment. Each truckload contains tens of thousands of liters of milk, and every batch must be verified to meet precise industrial standards before being accepted into the plant's supply chain. This initial phase involves a set of standardized protocols carried out in a dedicated receiving bay, equipped with specialized sampling and testing equipment. Upon arrival, the truck is docked to an unloading station, where automated lines connect directly to the tanker's valve. Before unloading can commence, operators perform a series of tests on a representative sample extracted from the tanker. This is done using a sanitized dipper or through a sample port using aseptic techniques to avoid contamination. The sample is then transferred to the plant's on-site quality control lab. Inside this lab, technicians first conduct a sensory inspection, evaluating the milk's color, smell, and presence of any visible particulates. While this step is basic, it's essential in immediately identifying any batches with gross spoilage or foreign contamination. The next series of tests are chemical and microbiological. A cryoscope is used to determine the freezing point of the milk, which helps identify dilution with water. Industrial condensed milk relies on unadulterated raw milk with tightly controlled fat and solids not fat contents. Any dilution affects the solids concentration required for the evaporation phase later on. Following this, infrared spectroscopy or mid-infrared analyzers are used to determine precise fat, protein, and lactose levels. These readings are compared against production targets, usually 3.5 to 4.0% fat and 8.5 to 9.0% SNF. If any component falls out of range, the milk may be either rejected or diverted to other dairy product lines. Another critical check is for microbial load. A rapid plate count, or ATP bioluminescence test, evaluates the total bacterial count per milliliter. Condensed milk production cannot start with high bacterial loads, as the concentration process would also concentrate any microbial byproducts, leading to off flavors and safety risks. Acceptable raw milk generally must have fewer than 100,000 colony-forming units per ml, with many plants enforcing even tighter limits. Additionally, presence of pathogens such as Listeria or Salmonella are monitored using immunoassay kits or PCR-based rapid tests. Antibiotic residue testing is also performed using either SNAP tests or microbial inhibition assays, since antibiotic contamination can disrupt the fermentation steps used in other dairy operations and might violate export regulations. If the sample passes all tests, the milk is cleared for unloading. The truck's contents are then pumped via sanitary stainless steel pipelines into raw milk holding tanks located within a temperature-controlled section of the facility. These tanks, typically ranging from 20,000 to 50,000 liters in capacity, are jacketed and agitated to maintain a constant temperature of around 4 degrees Celsius. At this stage, the milk is still unpasteurized and considered perishable, so time and temperature control are critical. The tanks are equipped with inline thermometers and CIP spray balls that will sanitize the internal surfaces between batches to prevent cross-contamination. The next step in the process is milk clarification and standardization. This is a pivotal moment where physical impurities and excess variability in composition are removed. The raw milk is fed from the storage tanks to a centrifugal clarifier, a high-speed rotating bowl separator that uses the density differences between milk solids and liquid to remove somatic cells, dirt, and other non-milk particles. The milk enters the spinning drum through a feed pipe, and under centrifugal force, heavier particles are flung outward against the bowl walls and discharged intermittently via sludge ejection ports. After clarification, the milk is sent to a cream separator. This piece of equipment operates similarly to the clarifier, but focuses on removing and isolating the cream layer from the skim milk portion. Depending on the desired end product specifications, some or all of the separated cream may be blended back in. This is where the standardization process comes into play. Condensed milk requires a tightly defined balance between fat content and total milk solids. Operators adjust this balance using inline blending systems, automated control loops equipped with flow meters and density sensors. The goal is to create a uniform milk base, typically around 8.5% fat and 22% total solids before it proceeds to pasteurization and evaporation. Any deviation at this stage would affect the efficiency of the next stages and could compromise the desired thickness, sweetness, and shelf life of the condensed milk. In more advanced factories, these composition adjustments are performed entirely by automated PLC systems. These use real-time data collected from inline sensors to control proportioning valves and regulate the mixing of cream and skim milk streams without any manual input. This level of automation not only ensures consistency, but reduces waste and energy use. The standardized milk is now homogeneous in composition, free of debris, and ready for thermal treatment. Before entering the pasteurizer, it may pass through a deaerator, a vacuum chamber that removes entrapped gases such as oxygen and carbon dioxide, which, if left in, could promote oxidation of fats and off flavors during storage. But up next is a step that changes the physical properties of the milk at a fundamental level. With the raw milk now cleaned, standardized, and compositionally balanced, it's time for it to undergo pasteurization and heat treatment, a step that prepares it for concentration without microbial risk or protein denaturation. This phase involves an intricate dance between temperature, pressure, and time, and it sets the stage for the transformative evaporation process that gives condensed milk its name. Now that the raw milk has been thoroughly received, clarified, and compositionally standardized, it is ready for thermal treatment. The next phase in the factory process is pasteurization, which is critical in destroying any pathogenic or spoilage microorganisms present in the milk. Pasteurization must be done with precise timing and temperature control to ensure microbial inactivation without damaging the milk's nutritional or functional properties, especially since this milk will soon undergo evaporation, which puts it under further thermal stress. To carry this out, the milk is directed from the holding tanks into a continuous flow, high-temperature, short-time pasteurization unit, which is the standard in industrial dairy processing. The HTST system typically consists of a series of plate heat exchangers that are engineered to raise the milk temperature to approximately 85 degrees Celsius for 15 to 20 seconds. This is hotter and slightly longer than conventional drinking milk pasteurization, as condensed milk requires greater microbial stability due to its extended shelf life. The process begins in the regeneration section of the plate heat exchanger, where incoming cold raw milk is preheated by outgoing pasteurized milk, allowing energy recovery and efficiency gains of up to 90%. The milk then moves through the heating section, where it is brought to the target temperature using hot water or steam circulated on the opposite side of the stainless steel plates. The timing of exposure is controlled by the flow rate and volume of the holding tubes, ensuring that every particle of milk receives uniform treatment. After pasteurization, the milk passes into a holding cell monitored by thermocouples and flow diversion valves. If the milk fails to reach or maintain the required pasteurization conditions, it is automatically diverted back to the raw milk tank for reprocessing. Once verified, the pasteurized milk is cooled again in the regeneration section, where it gives off its heat to the incoming raw milk, and then further chilled to around 60 degrees Celsius in preparation for the next crucial step, evaporation. Before entering the evaporator, the milk passes through a balance tank that helps maintain a constant feed rate into the evaporation system, stabilizing flow and avoiding temperature fluctuations that could cause burn-on or fouling inside the evaporator tubes. Now it's time to go into the evaporation stage, which is arguably the heart of the condensed milk production process. This is where the milk is physically transformed, thickened into a rich, viscous product through the removal of water. The goal here is to reduce the water content from its original 87% down to around 60%, achieving a final concentration of about 28% milk solids and 44% added sugar in the case of sweetened condensed milk. This is achieved through multi-effect vacuum evaporation, an energy-efficient process that allows for large-scale water removal without subjecting the milk to damaging high temperatures. The milk enters a multiple-effect falling film evaporator, which is the industry standard for large volume dairy processing. In this system, the pasteurized milk is introduced at the top of vertical stainless steel tubes where it forms a thin film as it flows downward. Simultaneously, steam is injected into adjacent chambers that surround the tubes, heating them indirectly. Because the evaporator is operated under vacuum, often at pressures around 70 to 100 millibar, the boiling point of the milk is reduced to around 55 degrees Celsius. This protects the sensitive proteins, sugars, and fats from heat-induced damage, preserving both flavor and nutritional quality. In a multi-effect setup, the vapor produced from one stage is used to heat the next stage, drastically improving energy efficiency. A typical 5-effect evaporator can remove over 85% of the water from milk with minimal energy input, thanks to this cascading reuse of thermal energy. The evaporated water is condensed and collected as waste heat condensate, which can later be recycled within the plant for cleaning processes or steam generation. Inside the evaporator, the thin film of milk continuously loses moisture as it falls. The combination of short residence time, low boiling point, and efficient heat transfer ensures that concentration occurs evenly and rapidly. By the time the milk reaches the bottom of the final effect, it has reached a viscous, concentrated state with a solid content of around 45%. At this point, it is discharged into an intermediate concentrate tank, where it is gently agitated and kept warm to prevent crystallization or skin formation on the surface. But the evaporation process alone does not fully define condensed milk as we know it, especially in the case of sweetened condensed milk. Once the desired solids concentration is achieved, the next critical step is the addition of sugar, which is not merely for taste, but serves as a functional preservative. The high sugar content lowers the water activity of the product to a point where microbial growth is virtually halted, granting it a long shelf life without refrigeration. The method of sugar addition must be extremely precise, as the wrong concentration can lead to issues like crystallization, viscosity problems, or even fermentation in rare cases. To do this, refined white sugar, typically sucrose, is added to the concentrated milk in the form of a hot sugar syrup. This syrup is prepared separately in jacketed mixing vessels, where dry granulated sugar is dissolved in water and heated to around 70 degrees Celsius. The syrup is filtered to remove any particulate matter and pumped into the concentrate tank under controlled flow rates. The typical formulation is around 46% sucrose by weight in the final product, which is determined by a combination of inline refractometers and density meters. The mixing of sugar syrup into the concentrate must be uniform to prevent localized crystallization and is often aided by low shear agitators that maintain homogeneity without introducing air. As the sugar is added, the milk becomes even more viscous and dense. At this point, the product's temperature is carefully maintained between 60 degrees Celsius and 65 degrees Celsius, as dropping below this range can initiate premature crystallization, while higher temperatures can scorch the milk solids. Once the sugar is fully integrated, the mixture is briefly held in a jacketed holding tank for a process known as equilibration, which allows any remaining air bubbles to rise and dissipate and gives time for the solution to reach equilibrium in terms of water activity and solute concentration. This marks the end of the thermal and compositional transformation stages. From a microbiological and physicochemical standpoint, the product is now shelf-stable, viscous, and chemically preserved by both heat treatment and high sugar concentration. However, it's not yet ready for packaging. There are still important steps to take involving cooling, crystallization control, and downstream finishing that are vital to achieving the smooth texture and glossy appearance that define high-quality condensed milk. With the concentrated sweetened milk now fully blended and equilibrated, the next critical phase in the condensed milk manufacturing process is controlled cooling and crystallization. This step is vital not only to achieving the desired texture and viscosity, but also to ensuring long-term product stability. If cooling is done too quickly or without proper control over nucleation, the lactose and sucrose in the product can crystallize into large, gritty particles. This not only affects mouthfeel, but can also lead to phase separation over time. To avoid this, the condensed milk is sent through a carefully engineered cooling and seeding system that promotes the formation of microcrystals, small, evenly distributed sugar crystals that give condensed milk its signature smooth, glossy consistency. The cooling system typically consists of scraped surface heat exchangers or jacketed tubular coolers. These systems are designed to handle highly viscous liquids and provide a high degree of thermal control. In scraped surface heat exchangers, the condensed milk flows through a cylindrical barrel while rotating blades constantly scrape the inner surface. This ensures that no product burns or sticks to the hot surface, and that the entire volume of milk is uniformly cooled. The cooling medium, usually chilled glycol or water, is circulated through the jacket, gradually lowering the milk temperature from around 65 degrees Celsius to 30-35 degrees Celsius. As the milk cools, it passes through a crystallization chamber where it is inoculated with fine lactose or sucrose seed crystals. These seed crystals are introduced in a controlled manner using a dosing system that meters out microscopic crystals with a high surface area. The goal is to initiate crystallization at a molecular level, encouraging the dissolved sugars to form consistent and extremely fine crystals rather than large, coarse ones. Agitators in the crystallization chamber are designed to promote gentle but thorough mixing, ensuring uniform distribution of the seed material without incorporating excess air, which could lead to oxidation or microbial contamination. Once seeded, the mixture is held at a stable crystallization temperature, typically around 30 degrees Celsius, for a period ranging from 30 to 90 minutes, depending on the batch size and product formulation. This resting period allows the crystals to grow slightly while remaining small and suspended, forming a delicate lattice within the viscous matrix of the milk. It is during this stage that the final texture of the condensed milk is locked in. Operators closely monitor the product's Brix value, viscosity, and temperature, using inline sensors and laboratory sampling to ensure that the crystallization proceeds according to specification. After the crystallization phase, the product enters the Dehauling stage. Despite all precautions taken during processing, the condensed milk will inevitably contain some entrapped air, either from mechanical mixing, seeding, or agitation. This air must be removed before packaging to prevent oxidation, which can degrade both flavor and color over time. Deaeration also helps improve fill accuracy during packaging, ensuring a stable and uniform product weight in each container. Deaeration is typically carried out in a vacuum deaerator tank. The condensed milk is pumped into the tank, which is maintained under a vacuum of around -0.8 bars. Inside the tank, the milk is spread into a thin film across a series of rotating trays or falling film surfaces, maximizing the exposed surface area. As the product spreads out under vacuum, dissolved gases and trapped air are released and drawn out by the vacuum pump system. In some systems, nitrogen gas is also bubbled through the product as a stripping agent to help displace oxygen more effectively. This process is continuously monitored with oxygen sensors to ensure minimal residual oxygen levels in the final product, typically less than 0.5 milligrams per litre. Once deaerated, the condensed milk is often passed through a final homogenization stage. While not strictly required in all formulations, homogenization is frequently used to improve product consistency, prevent fat separation, and extend shelf stability. In this process, the milk is forced through a narrow orifice under high pressure, usually between 100 to 150 bar, causing the fat globules to break down into much smaller sizes, typically less than 1 micron in diameter. This prevents creaming or separation during storage and gives the final product a more uniform mouthfeel. The homogenizer used in this step is typically a two-stage piston-type homogenizer. In the first stage, pressure is applied to break apart the fat globules. In the second stage, the product is passed through an impact ring to further disperse and stabilize the emulsion. This ensures that the fat remains evenly distributed throughout the viscous condensed milk matrix, even after months of storage on a shelf. The process must be carefully balanced to avoid over-shearing the product, which could break the sugar crystal structure and lead to syneresis or texture issues. With the product now fully processed, it moves to the packaging line. Before any milk enters a can or a tube, the packaging material itself must undergo preparation. Metal cans are the most common format for condensed milk, though plastic tubes and laminated pouches are also used depending on market demands. The cans arrive at the factory either as pre-formed containers or as rolled flat blanks that are formed and sealed on site using can-forming machinery. If using pre-formed cans, the first step is depalletizing and feeding. The cans are automatically unloaded from shipping pallets and fed into a cleaning system via conveyor belts. Here, they pass through a high-pressure air blower system that removes dust and debris. They may also pass through an inverted rinse tunnel that sprays them with sterile water or a mild sanitizing solution. Optical sensors verify that each can is intact and free of damage before it proceeds. The clean cans are then transported to the filling station, where they are indexed into position beneath nozzles connected to a positive displacement filler system. These filling machines are designed to handle thick, viscous liquids with high precision. A typical condensed milk filling machine includes a volumetric dosing mechanism that ensures every can receives the exact same quantity, usually around 397 grams, the standard retail size. Sensors ensure the nozzles do not drip or splash, and the filling process is conducted in a low oxygen environment to prevent post-process contamination. As cans are filled, they immediately move to the vacuum closing station. This is another critical step in ensuring product longevity. Before the lid is sealed, a vacuum is applied to the headspace in the can to remove residual air. This helps prevent oxidation and maintains the slight negative pressure required for a tight seal. The lid is then applied and hermetically sealed using a double seam seaming machine. This creates an airtight seal by mechanically folding and compressing the lid and can flange together in 2 operations. The quality of this seal is checked automatically using seam gauges and vision inspection systems to detect any defects or incomplete closures. After sealing, the cans enter a hot water bath or steam chamber for thermal holding. This step, known as in-can sterilization or thermal stabilization, involves heating the sealed cans to around 85 to 90 degrees Celsius for 15 to 20 minutes. This serves several functions. It neutralizes any residual microbes that may have entered during filling, helps equalize pressure inside the can, and further reduces the water activity of the product. The heating process is tightly controlled using a time temperature data logger to ensure consistency across batches. Once the thermal holding is complete, the cans are rapidly cooled using chilled water sprays or immersion tunnels. This quick cooling halts the cooking process and helps set the product structure inside the can. It also prevents over-darkening, which can occur due to Maillard reactions between milk proteins and sugars at elevated temperatures. The cans are then dried using air knives and conveyed to the labeling and coding area. Each can is now labeled with full product information, including nutritional facts, production batch codes, expiration dates, and allergen warnings. Laser coders or inkjet printers apply traceability codes directly onto the lid or bottom of each can, allowing for full tracking throughout the supply chain. These codes are critical for food safety as they allow for rapid recall or identification of affected batches in the rare event of a contamination issue. From here, the cans are packed into cartons or shrink-wrapped into bundles using automated case packers. The cartons are stacked onto pallets and wrapped with stretch film for transport. At this stage, finished condensed milk is subjected to final quality inspection, where random samples from each batch are tested for Brix value, fat content, microbial load, viscosity, and packaging integrity. Once the batch is cleared, it is released for distribution. With the cans now fully sealed, labeled, and palletized, the condensed milk moves into the final stretch of its industrial journey: post-production storage, distribution, and market readiness. While it may seem that the heavy lifting is over, these concluding steps are far more complex and technologically managed than they first appear. Factories invest significant resources to ensure that every can of condensed milk not only leaves the facility in perfect condition, but also maintains its quality throughout the entire shelf life, often up to 2 years or more. Immediately after packaging, pallets of condensed milk are transferred to temperature-controlled finished goods warehouses. The climate in these storage areas is tightly regulated, typically kept between 15 degrees Celsius and 25 degrees Celsius, with relative humidity under 60%. This environment prevents moisture accumulation on the can surfaces and limits the rate of any chemical reactions inside the product, such as non-enzymatic browning. Even though the condensed milk is shelf-stable, excessive heat over time can darken the color and subtly change the flavor profile. These storage conditions are monitored 24/7 using IoT-connected environmental sensors that send real-time data to the facility's central control system. Each pallet is barcoded with batch numbers and entered into a digital warehouse management system. This system not only tracks location and inventory levels, but also enforces FIFO protocols to ensure older batches are distributed before newer ones. The traceability codes printed earlier on the cans come into play again here. Every single unit can be traced back to its raw milk intake, processing parameters, operator ID, and time-stamped process logs. This full chain traceability is a critical part of modern food safety compliance. When orders are received from retailers, exporters, or institutional buyers, automated robotic pallet pickers retrieve the relevant stock and move it to the outbound shipping area. Here, it is loaded into refrigerated or insulated trucks, depending on the destination and regional climatic conditions. In many cases, international shipments involve placing pallets into reefer containers that maintain stable temperatures for transoceanic shipping routes. Upon arrival at the processing plant, sunflower seeds are subjected to a rigorous cleaning regimen designed to remove a variety of impurities that may have been introduced during harvesting and transportation. This initial phase is critical, as foreign materials such as soil, stones, plant debris, and metal fragments can compromise the efficiency of the extraction process and the quality of the final product. The cleaning process typically involves several stages, each employing specialized equipment tailored to eliminate specific types of contaminants. The first line of defense in the cleaning operation is the magnetic separator. This device utilizes powerful magnets to attract and remove ferrous metal particles from the stream of sunflower seeds. Metal contaminants can originate from various sources, including harvesting equipment and transport containers, and their removal is essential to prevent damage to downstream processing machinery and to ensure product safety. The seeds pass over or through magnetic plates or drums, where metallic impurities are captured and separated from the bulk material. Following magnetic separation, the seeds proceed to vibrating sieves or screens. These machines consist of perforated plates or mesh screens that oscillate at high frequencies, effectively sorting the seeds based on size and shape. Larger impurities, such as sticks, leaves, and oversized debris, are unable to pass through the screen openings and are thus separated from the smaller, uniform sunflower seeds. The vibration intensity and screen aperture sizes are carefully calibrated to optimize the removal of unwanted materials while minimizing the loss of viable seeds. To address the presence of denser contaminants like stones and clumps of soil, the cleaned seeds are then routed through destoners. Destoners operate on the principle of density separation, utilizing airflow and vibration to differentiate between heavier impurities and the lighter sunflower seeds. As the mixture is fed onto an inclined vibrating deck, air is blown through the material from below. The heavier stones resist the upward airflow and migrate to the higher end of the deck, where they are discharged, while the lighter seeds are carried by the vibration to the lower end for collection. This process effectively ensures that only clean seeds advance to the next stage of processing. After the comprehensive cleaning process, the sunflower seeds are ready for dehulling, also known as shelling. Sunflower seeds are encased in hard outer shells or hulls that constitute a significant portion of the seed's total weight. These hulls are low in oil content and can impede the extraction process if not removed. Therefore, dehulling is a crucial step aimed at increasing the efficiency of oil extraction and improving the quality of the resulting oil. The dehulling process begins with the conditioning of the seeds to facilitate the separation of the hulls from the kernels. Conditioning typically involves adjusting the moisture content of the seeds through controlled heating or humidification. Properly conditioned seeds have hulls that are more brittle and easier to crack, enhancing the effectiveness of the dehulling equipment. Once conditioned, the seeds are fed into dehulling machines, which employ mechanical forces to crack the hulls. One common type of dehuller is the centrifugal sheller, which uses a rotating impeller to hurl the seeds against a hard surface, causing the hulls to fracture upon impact. Another method involves the use of roller mills, where seeds pass between counter-rotating rollers that exert compressive and shear forces, breaking the hulls without damaging the kernels. The choice of dehulling equipment depends on factors such as seed variety, desired throughput, and specific plant configurations. Following the cracking of the hulls, the mixture of kernels and shell fragments undergoes a separation process to isolate the oil-rich kernels. This separation is typically achieved through a combination of aspiration and screening techniques. Aspiration involves the use of air streams to lift and remove the lighter hull fragments from the heavier kernels. The mixture is fed into an aspirator, where a controlled airflow lifts the less dense hulls away from the denser kernels, effectively segregating the two components. Screening may also be employed, utilizing vibrating screens with specific mesh sizes to further refine the separation based on particle size and shape. The efficiency of the dehulling and separation processes is paramount, as incomplete removal of hulls can lead to increased fiber content in the oil, affecting its clarity and stability. Moreover, residual hulls in the meal byproduct can diminish its nutritional value and marketability as animal feed. Therefore, processors often implement multiple passes through dehulling and separation equipment to achieve optimal results, balancing the trade-offs between processing time, energy consumption, and product quality. With the sunflower kernels now isolated and free from their hulls, they are ready to undergo further processing to extract the valuable oil contained within. The next stages involve mechanical pressing and/or solvent extraction, each with its own set of procedures and equipment designed to maximize oil yield and quality. These processes will be explored in detail in the subsequent sections, delving into the intricacies of transforming cleaned and dehulled sunflower seeds into the refined oil that reaches consumers worldwide. Now it's time to go into the core phase of sunflower oil manufacturing, the oil extraction process. This is where the golden liquid locked inside the sunflower kernels is separated and collected. The extraction phase typically uses one of two methods, or more commonly, a combination of both, for optimal oil recovery: mechanical pressing and solvent extraction. Each method has its own benefits and limitations, and modern sunflower oil factories are designed to seamlessly integrate these systems into a continuous, high-efficiency process that minimizes waste and maximizes yield. The first step in oil extraction is mechanical pressing, often referred to as expelling. In this process, the dehulled and cleaned sunflower kernels are conveyed into a series of screw presses, also known as oil expellers. These heavy-duty machines consist of a cylindrical barrel housing a rotating helical screw shaft. As the kernels are fed into the expeller from one end, the screw shaft compresses them with increasing pressure as they travel along the barrel. The space between the screw and the barrel gradually narrows, intensifying the pressure and causing the oil to be forced out through small perforations or slits in the barrel wall. This process is incredibly robust and continuous, with some industrial presses capable of handling several tons of seed per hour. However, mechanical pressing alone can only extract about 85% to 90% of the total oil content from sunflower seeds. The remaining 10% to 15% stays trapped in the pressed cake, a solid, fibrous byproduct that still contains a considerable amount of valuable oil. To retrieve this remaining oil and improve overall efficiency, factories employ solvent extraction. Before the solvent extraction phase begins, the pressed cake from the mechanical expeller must be properly prepared. This involves breaking the compacted cake into smaller, uniform pieces using a cake breaker or flaking mill. The flakes are then conveyed to a conditioning unit where they are heated to a specific temperature, usually between 60 to 80 degrees Celsius. This heating not only helps to soften the cell structure of the material, but also enhances the effectiveness of the solvent by improving oil solubility and fluidity. Once conditioned, the sunflower cake is fed into a continuous extractor, typically a horizontal rotary extractor or a loop extractor. In this large stainless steel apparatus, the cake is soaked with a food-grade solvent, most commonly hexane, which has an exceptional ability to dissolve oils. The cake moves slowly through the extractor on a perforated conveyor belt or through a series of baskets, while the solvent is sprayed from above and recirculated from below. As the hexane seeps through the material, it dissolves the residual oil, forming a solution known as micellar. This micellar, containing both oil and solvent, is then pumped out of the extractor and sent to a series of distillation units where the solvent is evaporated and recovered, leaving behind the crude sunflower oil. The evaporation process is conducted under vacuum and controlled heating conditions to ensure complete solvent recovery without degrading the oil. Simultaneously, the now oil-depleted cake, referred to as spent meal, is conveyed to a dissolventizing toaster. This equipment uses steam and indirect heat to remove any residual hexane from the meal, making it safe for use as high-protein animal feed. Next, let's look at the processing of crude sunflower oil, which, at this stage, is a deep amber liquid that contains several impurities, including free fatty acids, phospholipids, pigments, waxes, and trace metals. Though technically oil, this unrefined product is not yet suitable for cooking or bottling. It must be purified and stabilized through a multi-step refining process, which includes degumming, neutralization, bleaching, dewaxing, and deodorization. The first of these refining steps is degumming. In this phase, the crude oil is mixed with a small amount of water or a weak acid, such as citric or phosphoric acid. This causes the naturally occurring phospholipids, gums, to become hydrated and coagulate into a heavier phase that can be separated through centrifugation. The removal of these gums is crucial because they can contribute to off flavors, reduce shelf life, and interfere with further refining stages. The centrifuges used here operate at extremely high speeds, up to 5,000 revolutions per minute, creating centrifugal forces strong enough to separate even microscopic droplets and particles. Once degummed, the oil is subjected to neutralization, where it is treated with a caustic soda solution to remove free fatty acids. These acids can contribute to rancidity and reduce the oil's stability, so their removal is vital for producing a high-quality, shelf-stable product. The soda reacts with the free fatty acids to form soap stock, which is then separated from the oil via another round of centrifugation. The soap stock may be further processed into industrial byproducts such as lubricants or fatty acid distillates, ensuring minimal waste. Now it's time for the bleaching phase. Despite its name, this stage does not involve any chlorine or harsh chemicals. Instead, the oil is mixed with an adsorbent clay material, often activated bleaching earth or acid-activated bentonite, that binds with pigments, trace metals, and other unwanted compounds. The mixture is then heated under vacuum and passed through a filtration system where the spent clay is removed, leaving behind a visibly lighter oil. The objective of this step is not only to improve the color, but also to remove pro-oxidants and residual contaminants that could impact the oil's flavor or stability. But up next is one of the most temperature-sensitive and critical steps: dewaxing. Sunflower oil naturally contains waxes that, while harmless, can cause cloudiness or sedimentation when the oil is refrigerated or stored at low temperatures. To ensure crystal clear oil, particularly for use in transparent bottles, the dewaxing process is implemented. The oil is cooled gradually in a crystallization tank to allow waxes to solidify, and then passed through chilling filters or plate and frame filter presses. The solidified waxes are captured by the filter media and removed, leaving the oil with improved cold stability and clarity. Finally, the last refining step is deodorization. This process removes volatile compounds, including aldehydes and ketones, that can impart undesirable flavors and odors to the oil. Deodorization is carried out in a high vacuum, high temperature distillation column where the oil is subjected to steam distillation at temperatures between 180 to 240 degrees Celsius. The high temperature causes the volatile substances to evaporate, and the vacuum ensures they are swiftly removed from the system. Modern deodorization systems include structured packing and multiple stripping trays that allow for efficient steam-oil contact with minimal thermal degradation of the oil. The end product of this exhaustive refining sequence is a brilliant, light yellow, odorless oil with a neutral flavor and excellent oxidative stability, qualities that make it ideal for cooking, frying, baking, and use in processed foods. The refined sunflower oil is now ready for bottling or bulk packaging, depending on its intended application, whether destined for supermarket shelves or as an ingredient in snack foods, margarine, or ready-to-eat meals. The oil's journey from seed to bottle is far from over. Now it's time to explore the next critical phase in the industrial sunflower oil production process, the packaging and distribution stage. After undergoing extensive cleaning, pressing, solvent extraction, and refining, the sunflower oil is now fully processed, brilliant in clarity, neutral in flavor, and stable for both cooking and long-term storage. But before it can reach consumers or be used by food manufacturers, the oil must pass through highly automated and carefully controlled packaging systems. These systems are designed to maintain product integrity, optimize shelf life, and meet regulatory and commercial requirements for both retail and industrial distribution. Once the refined sunflower oil leaves the deodorizer, it is pumped into large stainless steel holding tanks. These tanks are equipped with inert gas blanketing systems, typically using nitrogen, to prevent oxidative degradation of the oil. Even trace amounts of oxygen can initiate rancidity, so maintaining a low oxygen environment in storage is critical. The tanks are also thermally insulated and often jacketed for temperature control, maintaining the oil at a stable range of around 25 to 30 degrees Celsius. This ensures that the oil remains fluid and clear, preventing cloudiness that could otherwise form during cooler storage conditions. From these storage tanks, the oil is directed via stainless steel pipelines to the packaging area. The transfer lines are equipped with positive displacement pumps and high sensitivity flow meters to ensure precise, consistent delivery volumes. Before entering the filling systems, the oil passes through final filtration units, often made up of multi-layer stainless steel mesh or polymer filter cartridges to capture any microscopic particulates that may have entered during tank storage. This guarantees that only the cleanest, crystal clear oil reaches the packaging stage. The packaging line is often separated into two main tracks. One for retail-sized bottles, typically ranging from 500 milliliters to 5 liters, and another for bulk containers, such as 20-liter jerry cans, 200-liter drums, or 1,000-liter intermediate bulk containers for industrial clients. The retail packaging line begins with empty bottles being loaded onto a conveyor, either manually or through robotic depalletizers. These bottles are usually made from food-grade PET and are blow molded on-site or sourced from specialized suppliers. Before filling, every bottle passes through a bottle rinser, where a jet of filtered, compressed air or ozonated water is sprayed inside to remove any dust or particles. This ensures microbiological and particulate cleanliness before the oil is introduced. The cleaned bottles are then transferred to multi-head volumetric or gravimetric filling machines. These high-speed machines, capable of filling up to several hundred bottles per minute, are calibrated to extreme accuracy, ensuring every bottle contains the precise labeled volume, no more, no less. The filled bottles are immediately capped by rotary capping machines, which place and tighten tamper-evident screw caps or snap-fit closures. Some systems integrate induction sealing, where a foil liner inside the cap is sealed to the bottle mouth using electromagnetic energy. This creates an airtight, tamper-proof barrier that preserves freshness and prevents leakage during transit. After capping, bottles pass through labelers that apply pressure-sensitive or shrink-sleeve labels. These labels are printed with brand information, nutritional facts, batch codes, and expiration dates using high-speed inkjet or laser coders, allowing for complete traceability of every unit. Following labeling, bottles proceed through automated inspection systems equipped with cameras and sensors that verify fill levels, cap integrity, label alignment, and code legibility. Any non-compliant bottles are automatically rejected via pneumatic arms into separate bins for rework. Approved bottles continue along the line to automated cartoning and case packing stations, where robotic arms place them into cardboard cartons, followed by case sealing with hot melt glue or tape. For bulk packaging, a separate line handles large volume containers. These containers are positioned under filling nozzles that are often suspended from load cells to ensure accurate weight-based filling. Bulk fillers must also incorporate anti-foaming and venting mechanisms to prevent air entrapment, especially at high flow rates. Once filled, containers are sealed with heavy-duty caps or tamper-evident seals and palletized for shipping. All packaging configurations, whether for retail or industrial use, are assigned unique identifiers linked to the master production batch and logged in the plant's ERP system. Now it's time to delve into the logistics and distribution chain, which plays an equally crucial role in maintaining the sunflower oil's quality and ensuring timely delivery to global markets. Once the packaged oil is palletized, it is moved via autonomous guided vehicles or forklifts to climate-controlled storage warehouses. These warehouses are designed for high throughput and efficient inventory turnover. Pallets are organized using barcoded location systems, and warehouse management software ensures that the oldest batches are shipped out first, following the FIFO principle. Transportation from the factory to distribution centers, wholesalers, retailers, or export terminals is typically conducted in temperature-regulated trucks or intermodal containers. For export shipments, ISO tank containers or food-grade flexi-tanks are used to transport sunflower oil in bulk volumes over long distances, often across continents. These tanks are insulated and equipped with inert gas blanketing systems to maintain oil stability during the journey. For local or regional deliveries, finished product pallets are shrink-wrapped, strapped, and loaded into trucks equipped with GPS tracking and real-time temperature monitoring. Each shipment includes digital delivery documents with QR codes or RFID tags that sync with customer inventory systems, facilitating seamless unloading and tracking upon arrival. Delivery confirmation, quality checks, and real-time feedback mechanisms are used to verify that every order arrives in optimal condition, both physically and chemically. But up next is one of the most critical dimensions of the modern sunflower oil industry: quality assurance and regulatory compliance. The food-grade nature of edible oil necessitates adherence to stringent quality standards at every stage of the process, from seed selection to final bottling. Every batch of sunflower oil is subjected to a comprehensive suite of analytical tests conducted in on-site laboratories or accredited third-party labs. These tests include parameters like free fatty acid levels, peroxide value, aniseidine value, color, moisture content, and soap residue, all of which provide a comprehensive snapshot of oil quality and stability. Gas chromatography is used to profile fatty acid composition, ensuring the oil meets the standard range for linoleic and oleic acid contents. Spectrophotometers analyze color and clarity, while Carl Fisher titration determines residual moisture. These tests not only guarantee regulatory compliance with international standards like Codex Alimentarius, the European Union Food Safety Directives, and the US FDA guidelines, but also help refine internal production protocols. If any parameter falls outside the accepted range, the affected batch is isolated and either reprocessed or discarded. Up next, we focus on one of the more overlooked yet incredibly vital components of sunflower oil production: byproduct utilization and factory process integration. Modern industrial sunflower oil facilities are designed not only to produce refined oil efficiently, but also to capitalize on every possible output from the sunflower seed itself. This means that even materials which, in earlier generations of oil production, may have been considered waste, are now valuable raw materials for secondary industries or reprocessed within the factory. One of the most important of these byproducts is the sunflower meal or cake that remains after the oil has been extracted. This dense, protein-rich substance is collected immediately following the dissolventizing process and cooled using air blast or counterflow cooling systems to bring the temperature down from over 100 degrees Celsius to ambient levels. This temperature drop is necessary to preserve protein quality and prevent mold growth during storage. The cooled meal is then ground into a uniform particle size using hammer mills or roller mills and passed through vibrating screens to remove any oversized clumps. Sunflower meal is widely used in the livestock and poultry industries as a valuable feed ingredient due to its high protein content and favorable amino acid profile. Factories that produce sunflower oil at scale often have integrated bagging or bulk loading systems for the meal, allowing it to be packaged into 25 or 50 kilogram bags or loaded into bulk silos for shipment in trucks and rail cars. Some facilities even have in-house pelletizing systems that compress the meal into pellets, which are easier to handle, store, and transport. Another byproduct generated during processing is the husk or hull removed during the dehulling stage. These hulls, although devoid of oil and low in protein, have significant value as a biomass fuel. Many sunflower oil factories have transitioned to using these hulls as a renewable energy source to generate heat or steam for use in the facility. The hulls are fed into biomass boilers equipped with particulate filters and emissions control systems where they are combusted cleanly and efficiently. The steam produced powers heat exchangers for oil refining processes like bleaching, deodorization, and dewaxing, reducing reliance on fossil fuels and lowering the factory's carbon footprint. In more advanced facilities, excess steam from the coal-fired boilers is also used to drive small steam turbines, generating on-site electricity that supports lighting, automation systems, and auxiliary equipment. This form of cogeneration enhances energy efficiency and contributes to the plant's sustainability targets. Some operations even sell surplus energy back to the local grid, turning what was once a waste product into a revenue stream. Water recycling is another critical area of integration. Given the extensive use of water in processes such as conditioning, steam generation, equipment washing, and degumming, a closed-loop water treatment system is essential. Wastewater from the plant is collected in large settling tanks, where solids are removed via sedimentation. The water then passes through biological treatment units and membrane filtration systems, such as reverse osmosis or ultrafiltration, to remove organic matter, oil residues, and chemical impurities. The treated water is reused in non-critical applications like boiler feed or equipment cleaning, drastically reducing freshwater consumption. Now turning to process automation, modern sunflower oil facilities operate as highly digitized environments where real-time data governs every aspect of production. Centralized control rooms equipped with HMI panels and SCADA systems provide operators with full visibility and control over temperature, pressure, flow rate, and other parameters at each processing step. Every sensor in the system, from tank-level monitors to flow meters and load cells, is networked to a control system that not only logs data for traceability, but also actively regulates inputs to maintain optimal efficiency. For example, if a temperature deviation is detected in a deodorization column, the SCADA system can automatically adjust the steam valve opening percentage to correct the temperature within seconds. Similarly, in the filling line, digital vision systems detect the fill level and reject any bottles that fall outside preset tolerances. This integration between mechanical systems and digital controls ensures the factory runs continuously with minimal human intervention, reducing errors and improving consistency. Predictive maintenance is another application of advanced automation in sunflower oil production. Vibration sensors, thermographic cameras, and acoustic monitors are placed on motors, gearboxes, pumps, and bearings to detect wear patterns long before failure occurs. The data is fed into AI-driven platforms that analyze trends and forecast the optimal time for maintenance. This prevents unplanned downtime, increases equipment lifespan, and maintains uninterrupted production flow. Inventory management and logistics are similarly digitized. Raw materials, finished oil, packaging supplies, and maintenance components are tracked using barcodes or RFID tags that interface with the plant's ERP system. This allows real-time monitoring of stock levels, automatic reordering when thresholds are reached, and optimized production scheduling based on available resources and demand forecasts. Finished goods are tracked through the entire supply chain, and shipping documents are generated automatically, reducing paperwork and human error. The process of butter production in a factory begins with the acquisition of raw cream, which is typically sourced from dairy farms. The cream must meet strict quality standards to ensure it is suitable for butter production. Upon arrival at the factory, the cream undergoes comprehensive testing to verify its fat content, microbial levels, and overall purity. This initial assessment ensures that only the highest quality cream enters the production line. Once approved, the cream is stored in large refrigerated tanks, where it is maintained at a precise temperature to preserve its freshness until processing begins. Standardization is the next critical step in butter production. This involves adjusting the fat content of the cream to a consistent level, usually around 40%, which is optimal for churning into butter. Advanced machinery is employed to blend cream with varying fat contents or to add skim milk as needed. This precise adjustment ensures uniformity in the final product. Standardization also allows factories to produce different types of butter, such as light or extra rich varieties, by altering the fat percentage accordingly. The standardized cream is then pasteurized to eliminate any harmful bacteria and to enhance shelf stability. Pasteurization involves heating the cream to a specific temperature for a set duration, followed by rapid cooling to prevent spoilage. After pasteurization, the cream enters the aging phase. This step is crucial for developing the desired texture and flavor profile of the butter. During aging, the cream is stored at a controlled temperature for several hours, allowing natural enzymes and lactic acid bacteria to work on the fat molecules. For cultured butter production, additional bacterial cultures are introduced during this stage to impart a richer, more complex flavor. The aging process can vary depending on the type of butter being produced, with some recipes requiring longer periods to achieve the desired characteristics. Once the cream has been adequately aged, it moves to the churning stage. In industrial settings, large-scale churns are used to efficiently process vast quantities of cream. The churning process separates the butterfat from the buttermilk through continuous agitation. As the cream is churned, the fat globules begin to coalesce, forming small grains of butter. These grains gradually grow larger as the churning continues, eventually forming a cohesive mass of butter. The buttermilk, which is the liquid component remaining after the fat solids have separated, is drained off and often used in other food products, such as baking ingredients or animal feed. Following churning, the butter mass undergoes washing to remove any residual buttermilk and impurities. Cold water is carefully sprayed over the butter while it is continuously agitated to ensure thorough cleaning. This step is vital for improving the texture and extending the shelf life of the butter. After washing, the butter is worked to achieve the desired consistency. If salted butter is being produced, salt is added at this stage to act as a preservative and enhance flavor. The amount of salt varies based on the specific product requirements and regional preferences. The working process involves kneading the butter to distribute the salt evenly and to expel any remaining water. The packaging phase is the next significant step in butter production. At this point, the butter is shaped into blocks, tubs, or sticks, depending on the intended market. Modern factories utilize automated equipment to shape and package the butter efficiently. Each piece is weighed precisely to ensure accurate portioning. Packaging materials are selected for their ability to protect the butter from environmental factors such as light, air, and moisture, which can degrade its quality. Common packaging options include foil-wrapped blocks, plastic tubs, and stick wrappers. The design of the packaging often incorporates branding elements and nutritional information to appeal to consumers. Throughout the entire production process, quality control measures are rigorously enforced to maintain the integrity of the butter. Multiple checks and tests are conducted at various stages to ensure compliance with safety and quality standards. Microbiological testing confirms the absence of harmful bacteria, while physical tests assess the texture and spreadability of the butter. Chemical analysis verifies the fat content and flavor profiles. Sensory evaluation panels may also assess the taste, aroma, and appearance of the butter to ensure it meets consumer expectations. Any batch that fails to meet these criteria is either reprocessed or discarded to uphold product quality. Factories implementing sustainable practices aim to minimize their environmental impact. Waste materials, such as the buttermilk separated during churning, can be further processed to create valuable byproducts like whey protein. Energy usage is optimized through the recovery of waste heat generated during thermal processes, such as pasteurization, which can be reused within the factory. Water used in washing and cleaning operations is treated before discharge to comply with environmental regulations. These efforts contribute to a more sustainable and eco-friendly production process. Technological advancements have significantly enhanced the efficiency and precision of butter production in factories. Computer-controlled systems monitor and adjust parameters such as temperature, speed, and timing during each stage of the process. Robotics and artificial intelligence are increasingly integrated into factory operations to improve accuracy and reduce human error. For example, automated sensors can detect inconsistencies in the cream's fat content during standardization and make real-time adjustments to correct them. These innovations not only streamline the production process, but also allow for greater customization and flexibility in meeting diverse market demands. Consumer trends play a pivotal role in shaping butter production strategies. With growing interest in health-conscious eating, there is an increasing demand for low-fat or plant-based alternatives. Factories respond by developing new recipes and production methods to cater to these emerging preferences. Transparency in sourcing and production practices is becoming increasingly important to consumers, leading factories to adopt traceability systems that provide detailed information about the origin and journey of their products. This builds trust and enhances brand loyalty among customers. The global market for butter is influenced by a variety of factors, including dietary habits, cultural preferences, and economic conditions. Factories must remain adaptable and responsive to these changes to stay competitive. They invest in research and development to innovate and improve their products continuously. Collaboration with suppliers, retailers, and consumers helps factories understand market needs and align their production strategies accordingly. By leveraging technology, adhering to quality standards, and embracing sustainable practices, butter factories aim to deliver superior products that meet and exceed customer expectations. In the context of industrial butter production, the procurement of raw cream is a meticulous process. Cream is sourced from dairy farms that adhere to stringent quality protocols. Upon arrival at the factory, the cream is tested for fat content, microbial levels, and overall purity. Approved cream is stored in refrigerated tanks at a precise temperature to maintain freshness. Standardization adjusts the fat content to approximately 40%, using advanced machinery to blend cream with varying fat contents or add skim milk as necessary. This step ensures uniformity in the final product and enables the production of different butter varieties by altering the fat percentage. Pasteurization follows standardization, involving heating the cream to a specific temperature for a set duration to eliminate harmful bacteria and enhance shelf stability. After pasteurization, the cream enters the aging phase, where it is stored at a controlled temperature for several hours to develop the desired texture and flavor. Cultured butter production introduces additional bacterial cultures during this stage to impart a richer flavor. Churning separates the butterfat from the buttermilk through continuous agitation, forming small grains of butter that grow larger as the process continues. The buttermilk is drained off and often utilized in other food products. Washing removes residual buttermilk and impurities from the butter mass using cold water while it is continuously agitated. Salt is added during the working process if producing salted butter, enhancing flavor and acting as a preservative. Automated equipment shapes and packages the butter into blocks, tubs, or sticks with precise weighing, ensuring accurate portioning. Packaging materials protect the butter from environmental factors, incorporating branding elements and nutritional information to appeal to consumers. Quality control measures are enforced throughout the production process, with multiple checks and tests ensuring compliance with safety and quality standards. Microbiological testing confirms the absence of harmful bacteria. Physical tests assess texture and spreadability, and chemical analysis verifies fat content and flavor profiles. Sensory evaluation panels assess taste, aroma, and appearance to meet consumer expectations. Sustainable practices minimize environmental impact, recycling waste materials, optimizing energy usage, and treating water before discharge. Technological advancements enhance efficiency and precision with computer-controlled systems, monitoring and adjusting parameters during production. Consumer trends shape production strategies, driving innovation in recipes and methods to meet health-conscious demands and build transparency through traceability systems. Collaboration with stakeholders helps factories understand market needs and align production strategies accordingly, delivering superior products that exceed customer expectations. Industrial butter production involves intricate steps and considerations, balancing tradition with innovation. From cream preparation to final packaging, every stage is meticulously controlled to ensure high-quality butter. Advanced technologies, adherence to quality standards, and sustainability initiatives enhance efficiency and reduce environmental impact. Adapting to consumer trends ensures relevance in a competitive market, demonstrating the industry's commitment to responsible and forward-thinking practices. Butter production in factories combines art and science, transforming simple cream into a beloved staple enjoyed worldwide. The journey of butter from cream to table showcases the complexity and sophistication involved in industrial-scale production. Precise control over every stage, rigorous quality assurance, and integration of modern technologies highlight the dedication to delivering a versatile and delicious product. This exploration reveals the detailed processes and considerations that define butter production in a factory setting. Cream acquisition begins with sourcing from dairy farms, adhering to quality protocols. Testing ensures fat content, microbial levels, and purity meet standards. Approved cream is stored in refrigerated tanks at controlled temperatures. Standardization adjusts fat content to 40% using advanced machinery, enabling uniformity and variety production. Pasteurization eliminates bacteria and enhances shelf stability through precise heating and cooling. Aging develops texture and flavor, with cultured butter benefiting from additional bacterial cultures. Churning separates butterfat from buttermilk, forming grains that grow larger during continuous agitation. Buttermilk is drained off for reuse in other food products. Washing removes impurities using cold water while agitating the butter mass. Salt is added during the working process for flavor enhancement and preservation. Automated equipment shapes and packages butter into blocks, tubs, or sticks, with precise weighing ensuring accurate portions. Packaging materials protect against environmental factors, incorporating branding and nutritional information. Quality control enforces safety and quality standards through microbiological testing, physical assessments, and chemical analyses. Sensory evaluations ensure taste, aroma, and appearance meet expectations. Sustainable practices minimize environmental impact by recycling waste, optimizing energy use, and treating water before discharge. Technological advancements enhance efficiency and precision, with computer-controlled systems monitoring production parameters. Consumer trends drive innovation in recipes and methods, promoting health-conscious alternatives and transparency through traceability systems. Collaboration with stakeholders aligns production strategies with market needs, delivering superior products exceeding customer expectations. The creation of mayonnaise in a factory is an intricate process that combines the precision of science with the artistry of culinary expertise. At its essence, mayonnaise is an emulsion, a delicate blend of oil, water, and egg yolks, stabilized by natural emulsifiers such as lecithin. This journey from raw ingredients to jarred condiment involves numerous steps, each meticulously controlled to ensure consistency, flavor, and safety. It all begins with the procurement of high-quality raw materials. Eggs, vegetable oil, vinegar, and various seasonings form the foundation of mayonnaise production. Eggs, particularly their yolks, are crucial because they contain lecithin, a natural emulsifier that binds oil and water together. These eggs must meet stringent standards for freshness and cleanliness before entering the facility. Similarly, the choice of oil is critical. It must be pure and flavorful, as it significantly influences the taste of the final product. Vinegar serves dual purposes, acting as both a preservative and a flavor enhancer. Additional seasonings like salt, sugar, mustard powder, or garlic extract may also be added depending on the desired variety. Once these ingredients arrive at the factory, they undergo rigorous testing to ensure compliance with quality specifications. Microbial contamination, pH levels, and chemical composition are carefully checked. Approved ingredients are then stored in large tanks or silos under controlled conditions to preserve their integrity until needed. Eggs are often pasteurized at this stage to eliminate any potential pathogens, ensuring the safety of the final product. The heart of mayonnaise production lies in the mixing process, where individual components are transformed into a smooth, creamy emulsion. Initially, egg yolks are blended with vinegar and seasonings in a specialized mixer. This mixture acts as the base, providing the foundation for the emulsion. As the blending continues, liquid vegetable oil is slowly introduced into the mix. The key here is gradual addition. Pouring the oil too quickly can destabilize the emulsion, leading to separation. Advanced machinery, equipped with precise flow control mechanisms, ensures that the oil is incorporated at just the right rate, maintaining stability throughout the process. During this phase, the mechanical action of the mixer helps break down the oil into microscopic droplets, dispersing them evenly within the aqueous phase. Lecithin present in the egg yolks plays a pivotal role here, acting as a bridge between the oil and water molecules to prevent them from separating. This step requires careful monitoring of temperature and speed to achieve optimal results. Too much heat can denature the proteins in the egg yolks, compromising the emulsion, while insufficient agitation might leave the mixture lumpy or inconsistent. Once the initial emulsion has been formed, further adjustments may be made to fine-tune the texture and flavor. Additional ingredients, such as stabilizers or thickeners, may be added to enhance the viscosity of the mayonnaise, ensuring it maintains its creamy consistency over time. Some manufacturers also incorporate antioxidants to extend shelf life and preserve freshness. These additions are done using automated systems that measure quantities with remarkable accuracy, guaranteeing uniformity across batches. After the mixing process is complete, the mayonnaise moves to the homogenization stage. Homogenization involves subjecting the mixture to intense pressure through narrow channels, breaking down any remaining large oil droplets into even smaller particles. This step not only improves the stability of the emulsion, but also enhances the smoothness and silkiness of the final product. Modern factories use sophisticated homogenizers capable of processing vast quantities of mayonnaise efficiently while maintaining consistent quality. Next comes the pasteurization phase, a critical step in ensuring the safety of the mayonnaise. Although the eggs have already been pasteurized earlier in the process, the entire mixture is heated to a specific temperature for a set period to eliminate any residual bacteria or microorganisms. Pasteurization also helps stabilize the flavors, allowing them to meld together harmoniously. After heating, the mayonnaise is rapidly cooled to prevent degradation of its texture or nutritional value. With the mayonnaise now fully prepared, it proceeds to the packaging stage. Here, advanced filling machines dispense precise amounts of the product into jars, bottles, or sachets, depending on the intended market. Packaging materials are chosen for their ability to protect the mayonnaise from light, air, and moisture, which could otherwise compromise its quality. For instance, opaque plastic containers or glass jars with tight-fitting lids are commonly used to shield the contents from external factors. Each package is sealed hermetically to ensure freshness until it reaches the consumer. Quality assurance is woven seamlessly into every aspect of mayonnaise production. Throughout the process, samples are regularly taken and analyzed to verify that the product meets all required standards. Microbiological tests confirm the absence of harmful bacteria, while sensory evaluations assess factors such as color, aroma, and taste. Physical properties such as viscosity and spreadability are also measured to ensure the mayonnaise performs well when used in culinary applications. Any deviations from established norms trigger immediate corrective actions, ensuring that only the highest quality mayonnaise leaves the factory. In addition to producing standard mayonnaise, many factories specialize in creating variations tailored to specific tastes and dietary preferences. Reduced fat versions substitute some of the oil with water or other ingredients to lower calorie content without sacrificing flavor. Low sodium options cater to health-conscious consumers, while organic or vegan alternatives appeal to those seeking more sustainable or plant-based choices. These specialty products require unique formulations and production techniques, showcasing the adaptability of modern manufacturing facilities. Sustainability plays a significant role in contemporary mayonnaise production. Factories increasingly focus on minimizing waste, conserving energy, and reducing environmental impact. Waste oils generated during production are recycled into biofuels or other useful byproducts, while water used in cleaning processes is treated before discharge to comply with ecological regulations. Energy-efficient equipment and renewable energy sources further contribute to greener operations. Moreover, sourcing ingredients responsibly, such as using cage-free eggs or sustainably harvested oils, aligns with growing consumer demand for ethically produced goods. Technological advancements continue to revolutionize the mayonnaise industry. Automation streamlines production lines, enabling faster throughput while maintaining exceptional quality. Artificial intelligence and machine learning algorithms optimize processes by predicting equipment maintenance needs, identifying inefficiencies, and suggesting improvements. Robotics handle repetitive tasks with unmatched precision, freeing human workers to focus on higher value activities. These innovations not only boost productivity, but also allow factories to respond swiftly to changing market demands. Consumer trends heavily influence the evolution of mayonnaise production. With increasing awareness about nutrition and wellness, there is a growing interest in healthier alternatives and transparent labeling. Manufacturers address these concerns by developing innovative recipes and providing detailed information about ingredient origins and production methods. Customization capabilities enable factories to produce niche products catering to regional preferences or emerging dietary fads, such as keto-friendly or gluten-free mayonnaises. Global trade dynamics also shape the way mayonnaise is manufactured. Export markets demand adherence to diverse regulatory frameworks, requiring factories to implement flexible systems capable of meeting varying international standards. Collaboration with suppliers, distributors, and retailers ensures alignment with global supply chains, facilitating timely delivery of products worldwide. Continuous investment in research and development keeps factories at the forefront of technological innovation, ensuring their competitiveness in an ever-evolving marketplace. Beyond the technical aspects of production, the cultural significance of mayonnaise cannot be overlooked. In many regions, it is more than just a condiment. It is a symbol of culinary tradition and innovation. From classic sandwiches to elaborate dressings, Mayonnaise serves as a versatile ingredient that enhances countless dishes. Its widespread popularity has driven manufacturers to explore new flavors and textures, expanding its appeal beyond traditional boundaries. For example, flavored varieties infused with herbs, spices, or even fruit extracts offer exciting options for adventurous cooks and diners alike. Factories also prioritize food safety above all else, implementing comprehensive protocols to mitigate risks at every stage of production. Hazard analysis and critical control points. Systems identify potential hazards and establish measures to prevent them. Regular audits and certifications ensure compliance with local and international regulations. Employee training programs emphasize hygiene practices and proper handling procedures, reinforcing a culture of safety throughout the organization. Packaging design plays a vital role in the marketing and distribution of mayonnaise. Modern factories invest heavily in developing attractive and functional packaging solutions that appeal to consumers while protecting the product. Innovations in material science have led to the creation of lightweight yet durable containers that reduce shipping costs and environmental impact. Resealable caps and squeezable bottles enhance user convenience, making it easier for customers to enjoy the product without compromising freshness. Supply chain management is another critical component of successful mayonnaise production. Efficient logistics ensure a steady flow of raw materials into the factory and finished goods out to retailers. Strategic partnerships with suppliers help secure reliable sources of high-quality ingredients, while relationships with distributors facilitate rapid delivery to diverse markets. Real-time data analytics enable factories to forecast demand accurately, optimizing inventory levels and reducing waste. Research and development remain central to the growth of the mayonnaise industry. Scientists and engineers continuously experiment with new formulations, processing techniques, and packaging technologies to improve product quality and sustainability. Emerging trends in biotechnology and fermentation offer promising avenues for enhancing flavor profiles and extending shelf life. Collaborations with academic institutions and research organizations provide valuable insights into cutting-edge developments that can be applied to commercial production. The economic impact of mayonnaise production extends far beyond the factory floor. It supports jobs in agriculture, transportation, retail, and related industries, contributing significantly to local and national economies. By investing in community initiatives and sustainable practices, manufacturers demonstrate their commitment to corporate responsibility and long-term viability. Programs aimed at reducing carbon footprints, conserving water, and promoting biodiversity align with broader societal goals of environmental stewardship. As consumer preferences evolve, so too does the nature of mayonnaise production. Health-conscious individuals seek products with fewer additives and artificial ingredients, driving manufacturers to adopt cleaner label approaches. Clear communication about ingredient sourcing and production methods builds trust and fosters loyalty among discerning customers. Educational campaigns highlighting the benefits of mayonnaise as part of a balanced diet further reinforce its position as a staple in kitchens worldwide. Finally, the future of mayonnaise production promises exciting possibilities. Advances in automation, digitalization, and artificial intelligence will likely transform traditional manufacturing processes, enabling greater efficiency and flexibility. Personalized nutrition platforms may one day allow consumers to customize their own mayonnaise blends based on individual dietary needs and preferences. Meanwhile, ongoing efforts to reduce environmental impact and promote social responsibility will ensure that mayonnaise remains a beloved and sustainable choice for generations to come. Through precise control of every stage, from ingredient preparation to final packaging, factories ensure that each jar of mayonnaise delivers consistent quality and satisfaction. This exploration reveals the depth and complexity behind the seemingly straightforward process of making mayonnaise, highlighting the dedication and expertise required to bring this indispensable condiment to tables everywhere. The production of olive oil in a factory is a meticulous process that combines ancient traditions with modern technology to create one of the world's most revered culinary staples. Olive oil, often referred to as liquid gold, has been cherished for millennia for its rich flavor, health benefits, and versatility in cooking. The journey from olive groves to bottling lines involves several intricate steps, each designed to preserve the natural qualities of the olives while ensuring consistency and quality. It all begins with the cultivation of olives, which are grown primarily in regions with Mediterranean climates such as Spain, Italy, Greece, and parts of North Africa. The choice of olive variety plays a significant role in determining the flavor profile of the final product. Different varieties produce oils with distinct characteristics. Some are fruity and mild, while others are robust and peppery. Harvesting typically occurs between late autumn and early winter when the olives reach their peak ripeness. Timing is crucial because underripe olives yield less oil, while overripe ones can lead to off flavors. Once harvested, the olives are transported to the factory where they undergo rigorous quality checks. These inspections ensure that only healthy, undamaged fruits are used in production. Any leaves, stems, or debris are removed during this stage to prevent contamination. The cleaned olives are then stored temporarily in ventilated containers to maintain freshness until processing begins. The first step in the factory is washing the olives. This process removes dirt, dust, and any remaining impurities from the surface of the fruit. Clean water is sprayed over the olives while they are gently agitated to ensure thorough rinsing. After washing, the olives proceed to the milling stage, where they are crushed into a paste. Traditionally, stone mills were used for this purpose, but modern factories employ stainless steel crushers or hammer mills for greater efficiency. The goal is to break down the cell walls of the olives, releasing the oil trapped inside. Following milling, the olive paste moves to the malaxation phase. Malaxation involves slowly stirring the paste at a controlled temperature to allow small droplets of oil to coalesce into larger ones. This step is critical because it enhances the extraction rate and improves the quality of the oil by promoting better separation of solids and liquids. The duration of malaxation varies depending on factors such as olive variety and desired flavor profile, but it typically lasts between 20 and 40 minutes. After malaxation, the next step is decantation, where the olive paste is separated into its three main components: oil, water, and solid residue known as pomace. In traditional methods, this was achieved using centrifuges or pressing systems. Modern factories predominantly use horizontal decanter centrifuges, which spin the paste at high speeds to separate the heavier solid particles from the lighter liquid phases. The resulting mixture of oil and water is further refined in a second stage centrifuge, which separates the oil completely from any remaining water or fine particles. At this point, the crude olive oil undergoes additional treatments to refine its quality. Filtration is often employed to remove any residual suspended solids, producing a clearer and more stable product. Some manufacturers also implement cold filtration techniques to preserve the natural flavors and aromas of the oil. For extra virgin olive oil, minimal processing is preferred to retain its superior taste and nutritional value. However, lower grade oils may be subjected to chemical refining processes to improve clarity, color, and shelf life. Storage is another critical aspect of olive oil production. Once extracted, the oil is transferred to large stainless steel tanks where it is kept at controlled temperatures to prevent oxidation and degradation. These tanks are equipped with inert gas systems to displace oxygen, further protecting the oil's quality. During storage, the oil continues to settle, allowing any remaining microscopic particles to sink to the bottom of the tank. Periodic sampling and analysis ensure that the oil maintains its desired characteristics throughout this period. Packaging represents the final stage of the production process. Olive oil is bottled in various sizes and formats. ranging from small glass bottles to bulk plastic containers, depending on the target market. Packaging materials are chosen for their ability to shield the oil from light, air, and moisture, which can negatively affect its quality. Dark-colored glass or opaque plastic bottles are commonly used to protect against UV exposure, while tight-fitting caps ensure an airtight seal. Labels provide important information about the oil's origin, grade, and nutritional content, helping consumers make informed purchasing decisions. Quality control is woven into every aspect of olive oil production. Throughout the process, samples are regularly taken and analyzed to verify compliance with strict international standards. Sensory evaluations assess factors such as aroma, taste, and mouthfeel, ensuring the oil meets expectations for its designated grade. Chemical analyses measure parameters like acidity levels, peroxide values, and fatty acid composition to confirm purity and authenticity. Any deviations from established norms trigger immediate corrective actions, guaranteeing that only the highest quality olive oil reaches the market. In addition to producing standard olive oil, many factories specialize in creating premium varieties tailored to specific tastes and dietary preferences. Extra virgin olive oil, considered the finest grade, is produced using mechanical means only, without heat or chemicals, to preserve its natural flavors and antioxidants. Virgin olive oil undergoes slightly more processing, but still retains much of its original character. Refined olive oil, on the other hand, is treated with chemical agents to neutralize defects and achieve uniformity in taste and appearance. Specialty oils infused with herbs, spices, or citrus extracts offer unique flavor profiles that appeal to adventurous cooks and diners alike. Sustainability is increasingly becoming a priority in olive oil production. Factories adopt eco-friendly practices to minimize waste, conserve resources, and reduce environmental impact. Pomace, the solid residue left after extraction, is often recycled into biofuels or animal feed, reducing landfill contributions. Water used in cleaning processes is treated before discharge to comply with ecological regulations. Energy-efficient equipment and renewable energy sources further contribute to greener operations. Moreover, sourcing olives responsibly, such as supporting local farmers who practice sustainable agriculture, aligns with growing consumer demand for ethically produced goods. Technological advancements continue to revolutionize the olive oil industry. Automation streamlines production lines, enabling faster throughput while maintaining exceptional quality. Artificial intelligence and machine learning algorithms optimize processes by predicting equipment maintenance needs, identifying inefficiencies, and suggesting improvements. Robotics handle repetitive tasks with unmatched precision, freeing human workers to focus on higher value activities. These innovations not only boost productivity, but also allow factories to respond swiftly to changing market demands. Consumer trends heavily influence the evolution of olive oil production. With increasing awareness about nutrition and wellness, there is a growing interest in healthier alternatives and transparent labeling. Manufacturers address these concerns by developing innovative formulations and providing detailed information about ingredient origins and production methods. Customization capabilities enable factories to produce niche products catering to regional preferences or emerging dietary fads, such as organic or keto-friendly options. Global trade dynamics also shape the way olive oil is manufactured. Export markets demand adherence to diverse regulatory frameworks, requiring factories to implement flexible systems capable of meeting varying international standards. Collaboration with suppliers, distributors, and retailers ensures alignment with global supply chains, facilitating timely delivery of products worldwide. Continuous investment in research and development keeps factories at the forefront of technological innovation, ensuring their competitiveness in an ever-evolving marketplace. Beyond the technical aspects of production, the cultural significance of olive oil cannot be overlooked. In many regions, it is more than just a cooking ingredient. It is a symbol of heritage and tradition. From drizzling it over fresh bread to using it as the base for elaborate sauces, olive oil serves as a versatile foundation for countless dishes. Its widespread popularity has driven manufacturers to explore new applications and presentations, expanding its appeal beyond traditional boundaries. Factories also prioritize food safety above all else, implementing comprehensive protocols to mitigate risks at every stage of production. Hazard analysis and critical control. Point systems identify potential hazards and establish measures to prevent them. Regular audits and certifications ensure compliance with local and international regulations. Employee training programs emphasize hygiene practices and proper handling procedures, reinforcing a culture of safety throughout the organization. Packaging design plays a vital role in the marketing and distribution of olive oil. Modern factories invest heavily in developing attractive and functional packaging solutions that appeal to consumers while protecting the product. Innovations in material science have led to the creation of lightweight yet durable containers that reduce shipping costs and environmental impact. Resealable caps and pour spouts enhance user convenience, making it easier for customers to enjoy the product without compromising freshness. Supply chain management is another critical component of successful olive oil production. Efficient logistics ensure a steady flow of raw materials into the factory and finished goods out to retailers. Strategic partnerships with suppliers help secure reliable sources of high-quality olives, while relationships with distributors facilitate rapid delivery to diverse markets. Real-time data analytics enable factories to forecast demand accurately, optimizing inventory levels and reducing waste. Research and development remain central to the growth of the olive oil industry. Scientists and engineers continuously experiment with new formulations, processing techniques, and packaging technologies to improve product quality and sustainability. Emerging trends in biotechnology and fermentation offer promising avenues for enhancing flavor profiles and extending shelf life. Collaborations with academic institutions and research organizations provide valuable insights into cutting-edge developments that can be applied to commercial production. The economic impact of olive oil production extends far beyond the factory floor. It supports jobs in agriculture, transportation, retail, and related industries, contributing significantly to local and national economies. By investing in community initiatives and sustainable practices, manufacturers demonstrate their commitment to corporate responsibility and long-term viability. Programs aimed at reducing carbon footprints, conserving water, and promoting biodiversity align with broader societal goals of environmental stewardship. As consumer preferences evolve, so too does the nature of olive oil production. Health-conscious individuals seek products with fewer additives and artificial ingredients, driving manufacturers to adopt cleaner label approaches. Clear communication about ingredient sourcing and production methods builds trust and fosters loyalty among discerning customers. Educational campaigns highlighting the benefits of olive oil as part of a balanced diet further reinforce its position as a staple in kitchens worldwide. Finally, the future of olive oil production promises exciting possibilities. Advances in automation, digitalization, and artificial intelligence will likely transform traditional manufacturing processes, enabling greater efficiency and flexibility. Personalized nutrition platforms may one day allow consumers to customize their own olive oil blends based on individual dietary needs and preferences. Meanwhile, ongoing efforts to reduce environmental impact and promote social responsibility will ensure that olive oil remains a beloved and sustainable choice for generations to come. Through precise control of every stage, from olive cultivation to final packaging, factories ensure that each bottle of olive oil delivers consistent quality and satisfaction. This exploration reveals the depth and complexity behind the seemingly straightforward process of making olive oil, highlighting the dedication and expertise required to bring this indispensable liquid to tables everywhere. The production of whipped cream in a factory is a highly refined process that combines traditional techniques with modern technology to create one of the most beloved and versatile dairy products. Whipped cream, known for its light, airy texture and rich flavor, has become an essential ingredient in desserts, beverages, and culinary creations worldwide. The journey from raw materials to finished product involves several intricate steps, each meticulously controlled to ensure consistency, quality, and safety. It all begins with the procurement of high-quality cream, which serves as the foundation of whipped cream production. Cream is typically sourced from fresh milk, separated through centrifugation or other mechanical processes to concentrate the fat content. For whipped cream, cream with a fat content of around 35% is ideal, as it provides the necessary structure and stability when aerated. The cream must meet stringent quality standards, including checks for purity, fat content, and microbial levels before entering the factory. Once approved, the cream is stored in refrigerated tanks at a precise temperature to preserve its freshness until processing begins. Upon arrival at the factory, the cream undergoes rigorous testing to ensure it meets the required specifications. This includes microbiological testing to confirm the absence of harmful bacteria, chemical analysis to verify fat content, and sensory evaluations to assess flavor and aroma. Approved cream is then standardized to ensure uniformity across batches. Standardization involves adjusting the fat content to the desired level using advanced machinery that blends cream with varying fat contents or adds skim milk as needed. This step is critical for maintaining consistent product quality and enabling customization for different varieties of whipped cream. After standardization, the cream moves to the pasteurization stage. Pasteurization is a crucial step in ensuring the safety and shelf life of the whipped cream. During this process, the cream is heated to a specific temperature for a set duration, followed by rapid cooling. This eliminates any harmful microorganisms while preserving the cream's natural flavors and nutritional properties. Pasteurized cream is then stored at a controlled temperature to maintain its quality until further processing. The next phase in whipped cream production is stabilization. To enhance the cream's ability to hold air and maintain its fluffy texture, stabilizers such as guar gum, carrageenan, or xanthan gum may be added. These ingredients help prevent separation and improve the cream's whipping properties. Emulsifiers like mono and diglycerides may also be incorporated to ensure smooth blending and even distribution of fat globules during aeration. The choice of stabilizers and emulsifiers depends on the desired final product and regulatory requirements in different markets. Once stabilized, the cream proceeds to the whipping stage, where it is transformed into its characteristic light and airy form. In industrial settings, this is achieved using large-scale whipping machines capable of processing vast quantities of cream efficiently. The whipping process involves introducing air into the cream while agitating it at a controlled speed and temperature. As the cream is whipped, the fat globules coalesce, forming a network that traps air bubbles, creating the signature texture of whipped cream. The degree of aeration is carefully monitored to achieve the desired density and volume. During whipping, additional ingredients such as sugar, vanilla extract, or other flavorings may be incorporated to enhance the taste and appeal of the whipped cream. Sugar not only sweetens the product, but also helps stabilize the foam by increasing viscosity and improving bubble formation. Flavorings are carefully selected and measured to ensure they complement the natural richness of the cream without overpowering it. Some manufacturers produce flavored variations, such as chocolate, coffee, or fruit-infused whipped creams, catering to diverse consumer preferences. After whipping, the cream is cooled to stabilize its structure and prevent degradation. Cooling is typically done in a controlled environment to ensure the whipped cream retains its shape and texture. At this stage, the product may undergo further adjustments to fine-tune its consistency and appearance. Advanced machinery is used to measure parameters such as overrun and firmness. ensuring the whipped cream meets the desired specifications. Packaging represents the final stage of whipped cream production. Modern factories utilize automated equipment to dispense precise amounts of the product into various formats, including aerosol cans, plastic tubs, or flexible pouches. Aerosol packaging is particularly popular due to its convenience and ease of use, allowing consumers to spray the whipped cream directly onto their favorite foods. Nitrous oxide is often used as the propellant in aerosol cans, providing both the means of dispensing and contributing to the cream's light texture. Packaging materials are chosen for their ability to protect the whipped cream from light, air, and moisture, which can affect its quality. Labels provide important information about the product's ingredients, nutritional content, and usage instructions, helping consumers make informed choices. Quality control is an integral part of whipped cream production, implemented throughout every stage of the process. Samples are regularly taken and analyzed to verify compliance with strict international standards. Microbiological tests confirm the absence of harmful bacteria, while physical and chemical analyses assess factors such as overrun, firmness, and fat content. Sensory evaluations evaluate the whipped cream's flavor, aroma, and texture to ensure it meets consumer expectations. Any deviations from established norms trigger immediate corrective actions, guaranteeing that only the highest quality whipped cream reaches the market. In addition to producing standard whipped cream, many factories specialize in creating premium varieties tailored to specific tastes and dietary preferences. Low-fat or non-dairy alternatives cater to health-conscious consumers, while organic options appeal to those seeking more sustainable choices. Specialty flavors and textures offer exciting options for adventurous cooks and diners alike. These variations require unique formulations and production techniques, showcasing the adaptability of modern manufacturing facilities. Sustainability plays a significant role in contemporary whipped cream production. Factories increasingly focus on minimizing waste, conserving resources, and reducing environmental impact. Waste cream generated during production is recycled into animal feed or biofuels, while water used in cleaning processes is treated before discharge to comply with ecological regulations. Energy-efficient equipment and renewable energy sources further contribute to greener operations. Moreover, sourcing cream responsibly, such as supporting local farmers who practice sustainable agriculture, aligns with growing consumer demand for ethically produced goods. Technological advancements continue to revolutionize the whipped cream industry. Automation streamlines production lines, enabling faster throughput while maintaining exceptional quality. Artificial intelligence and machine learning algorithms optimize processes by predicting equipment maintenance needs, identifying inefficiencies, and suggesting improvements. Robotics handle repetitive tasks with unmatched precision, freeing human workers to focus on higher value activities. These innovations not only boost productivity, but also allow factories to respond swiftly to changing market demands. Consumer trends heavily influence the evolution of whipped cream production. With increasing awareness about nutrition and wellness, there is a growing interest in healthier alternatives and transparent labeling. Manufacturers address these concerns by developing innovative formulations and providing detailed information about ingredient origins and production methods. Customization capabilities enable factories to produce niche products catering to regional preferences or emerging dietary fads, such as keto-friendly or gluten-free options. Global trade dynamics also shape the way whipped cream is manufactured. Export markets demand adherence to diverse regulatory frameworks, requiring factories to implement flexible systems capable of meeting varying international standards. Collaboration with suppliers, distributors, and retailers ensures alignment with global supply chains, facilitating timely delivery of products worldwide. Continuous investment in research and development keeps factories at the forefront of technological innovation, ensuring their competitiveness in an ever-evolving marketplace. Beyond the technical aspects of production, The cultural significance of whipped cream cannot be overlooked. In many regions, it is more than just a topping. It is a symbol of indulgence and celebration. From birthday cakes to holiday feasts, whipped cream serves as a versatile ingredient that enhances countless dishes. Its widespread popularity has driven manufacturers to explore new applications and presentations, expanding its appeal beyond traditional boundaries. Factories also prioritize food safety above all else, implementing comprehensive protocols to mitigate risks at every stage of production. Hazard analysis and critical control. Point systems identify potential hazards and establish measures to prevent them. Regular audits and certifications ensure compliance with local and international regulations. Employee training programs emphasize hygiene practices and proper handling procedures, reinforcing a culture of safety throughout the organization. Packaging design plays a vital role in the marketing and distribution of whipped cream. Modern factories invest heavily in developing attractive and functional packaging solutions that appeal to consumers while protecting the product. Innovations in material science have led to the creation of lightweight yet durable containers that reduce shipping costs and environmental impact. Resealable caps and ergonomic handles enhance user convenience, making it easier for customers to enjoy the product without compromising freshness. Supply chain management is another critical component of successful whipped cream production. Efficient logistics ensure a steady flow of raw materials into the factory and finished goods out to retailers. Strategic partnerships with suppliers help secure reliable sources of high-quality cream, while relationships with distributors facilitate rapid delivery to diverse markets. Real-time data analytics enable factories to forecast demand accurately, optimizing inventory levels and reducing waste. Research and development remain central to the growth of the whipped cream industry. Scientists and engineers continuously experiment with new formulations, processing techniques, and packaging technologies to improve product quality and sustainability. Emerging trends in biotechnology and fermentation offer promising avenues for enhancing flavor profiles and extending shelf life. Collaborations with academic institutions and research organizations provide valuable insights into cutting-edge developments that can be applied to commercial production. The economic impact of whipped cream production extends far beyond the factory floor. It supports jobs in agriculture, transportation, retail, and related industries, contributing significantly to local and national economies. By investing in community initiatives and sustainable practices, manufacturers demonstrate their commitment to corporate responsibility and long-term viability. Programs aimed at reducing carbon footprints, conserving water, and promoting biodiversity align with broader societal goals of environmental stewardship. As consumer preferences evolve, so too does the nature of whipped cream production. Health-conscious individuals seek products with fewer additives and artificial ingredients, driving manufacturers to adopt cleaner label approaches. Clear communication about ingredient sourcing and production methods builds trust and fosters loyalty among discerning customers. Educational campaigns highlighting the benefits of whipped cream as part of a balanced diet further reinforce its position as a staple in kitchens worldwide. Finally, the future of whipped cream production promises exciting possibilities. Advances in automation, digitalization, and artificial intelligence will likely transform traditional manufacturing processes, enabling greater efficiency and flexibility. Personalized nutrition platforms may one day allow consumers to customize their own whipped cream blends based on individual dietary needs and preferences. Meanwhile, ongoing efforts to reduce environmental impact and promote social responsibility will ensure that whipped cream remains a beloved and sustainable choice for generations to come. Through precise control of every stage, from cream procurement to final packaging, factories ensure that each container of whipped cream delivers consistent quality and satisfaction. This exploration reveals the depth and complexity behind the seemingly straightforward process of making whipped cream, highlighting the dedication and expertise required to bring this indispensable product to tables everywhere. The industrial processing of honey begins not within the walls of the factory, but at the apiaries, where honeybees forage, collect nectar, and begin the complex enzymatic process of transforming floral sugars into the thick, golden liquid we know as honey. Factory-scale honey production starts with the careful coordination between contracted beekeepers and processing plants, which work together to supply bulk honey at a scale large enough to support mass distribution. The first step in the factory process involves the reception and inspection of raw honey as it arrives from the beekeepers' extraction sites. Raw honey is typically delivered in large food-grade steel drums or plastic totes, each capable of holding hundreds of pounds of honey. These containers arrive sealed, labeled with origin data, floral source if known, and batch tracking codes. Upon arrival at the honey processing facility, each container is unloaded onto the receiving dock, where a team of technicians begins the initial quality assurance process. This is far more than a visual check. Industrial honey processors must guarantee that the incoming product is pure, unadulterated, and meets strict legal and food safety standards. The drums are first sampled using a specialized honey sampling spear, a long stainless steel tube designed to pierce through the viscous mass and extract a vertical core from top to bottom. This is essential because honey can stratify with moisture content, color, and crystallization levels varying from top to bottom. The extracted sample is then homogenized and sent to the quality control laboratory. Here, a battery of tests is performed. Moisture content is measured using refractometers, which determine how much water is present in the honey. Legal standards require honey to contain no more than 20% moisture to prevent fermentation. Beyond moisture testing, analysts perform pollen analysis to verify floral sources and geographic origin, which is important for regulatory labeling and for upholding claims like clover honey or orange blossom honey. Additional tests, such as electrical conductivity, help differentiate between nectar and honeydew honeys, while HMF levels, or hydroxymethyl furfural, are checked to ensure the honey hasn't been exposed to excessive heat during prior storage or transit. High-performance liquid chromatography may also be used to detect the presence of added sugars, which would indicate adulteration and result in immediate rejection of the batch. Once a drum passes inspection and is approved for processing, it is moved to the uncrystallization station. Raw honey can crystallize over time, particularly when stored in cooler environments or when the floral source is rich in glucose. Crystallized or partially crystallized honey must be reliquefied before it can be filtered or blended. This is achieved by placing the drums in heated chambers or warm water baths, known as hot rooms, where they are gently warmed to temperatures around 95 to 110 degrees Fahrenheit. This temperature range is sufficient to melt crystals without degrading the honey's delicate aromatic and enzymatic properties. Large facilities often use drum heating tunnels that can accommodate dozens of drums at a time. These tunnels employ radiant heat panels and convection fans that maintain a steady, uniform temperature throughout the enclosure. Temperature probes are inserted into each drum to ensure that internal temperatures rise slowly and evenly, preventing localized overheating which could darken the honey or degrade its quality. This gentle warming process can take anywhere from 24 to 72 hours, depending on the degree of crystallization and the initial temperature of the honey when it arrived. Now it's time to go into the liquefaction and transfer stage, where the now softened honey is pumped out of the drums and into the factory's primary processing line. This step requires specialized food-grade pumps capable of handling thick, sticky materials without introducing air bubbles or damaging the honey's texture. Positive displacement pumps, such as rotary lobe or progressive cavity pumps, are commonly used for this purpose. These pumps are designed to move viscous fluids at a steady rate without causing foaming or aeration, which can negatively impact downstream processing. As the honey is pumped from each drum, it passes through heated stainless steel pipelines that maintain a consistent temperature, usually around 110 to 120 degrees Fahrenheit, to keep the honey fluid during transit. The pipelines are insulated to minimize heat loss, and the entire system is cleaned between batches using CIP or clean-in-place systems, which circulate hot water and food-safe cleaning agents to maintain sanitary conditions. Valves and flow meters are used to control how much honey enters the next phase, which is usually a settling or holding tank. These tanks are large vertical silos equipped with gentle agitation paddles to keep the honey uniform without whipping air into it. At this stage, the honey is allowed to rest briefly, giving suspended particles like wax fragments, bee parts, or pollen clumps time to rise or settle. Some facilities incorporate slow-flow decanting chambers or skimming belts that remove surface foam and floating debris. The goal here is to prepare the honey for the critical filtration stage without exposing it to excessive agitation or temperature shifts, which could compromise quality. But up next is the filtration stage, one of the most technically controlled steps in factory honey processing. The challenge with filtering honey lies in removing impurities while preserving beneficial properties such as flavor, aroma, and trace pollen content. To accomplish this, processors use a series of progressively finer filters, starting with coarse metal mesh screens and moving to finer, micron-level filtration pads or cartridges. Initially, the honey flows through vibratory sieve filters or centrifugal strainers that remove large debris, including chunks of wax or bee remnants. These are often equipped with auto-cleaning screens that rotate or vibrate to prevent clogging. After coarse filtering, the honey enters a fine filtration system. Depth filters composed of cellulose or food-grade polypropylene are commonly used. These filters remove particles as small as 5 to 10 microns, including residual wax, dust, and crystallized sugar particles that could initiate recrystallization in the final product. To aid this process, the honey is maintained at a precise temperature of about 120 to 130 degrees Fahrenheit, warm enough to reduce viscosity and improve flow through filters, but not so hot as to destroy heat-sensitive enzymes or antioxidants. Inline temperature sensors and automated control panels ensure that every gallon of honey is processed under identical thermal conditions. Some advanced facilities even use vacuum-assisted filtration to further reduce the need for high temperatures, thereby preserving more of the honey's raw characteristics. Once filtration is complete, the honey is collected in large stainless steel blending tanks. These tanks are used to homogenize different batches of honey, standardize flavor profiles, and adjust final parameters such as color and clarity. Mixing paddles rotate at slow, controlled speeds to avoid aeration while ensuring a uniform blend. It's at this stage that some producers may add trace amounts of previously tested and approved batches to maintain flavor consistency across large volumes, especially if multiple floral sources are involved. Now it's time to explore the homogenization process in more detail, as this step plays a pivotal role in ensuring that every bottle or jar of honey pulled from the line is virtually identical in texture, color, and taste. Honey, being a natural product, can vary widely between batches due to differences in nectar sources, collection times, and even seasonal variations. To manage these inconsistencies, processors rely on computer-controlled blending protocols that match incoming honey against established reference standards. Before blending begins, technicians perform sensory and analytical testing on the batch, including color measurement using the Fund scale, which classifies honey from water white to dark amber. Flavor notes are assessed by trained sensory panels or electronic nose devices while moisture and acidity levels are verified to determine blending ratios. If a batch is slightly darker than the standard product line, a portion of lighter honey is added to balance the color. If a batch is too viscous, a blend with a slightly higher moisture content is introduced to bring the final viscosity within specification. Mixing tanks used in this process are often jacketed with warm water or glycol to maintain the blending temperature at a steady 110 to 120 degrees Fahrenheit. Internal baffles guide the flow of honey, ensuring thorough integration without the formation of dead zones or stratification. The tanks are usually equipped with inline sensors that continuously monitor parameters like Brix, viscosity, and turbidity. The blending cycle may take several hours for large volumes, and throughout the process, automated samplers pull small amounts at regular intervals to verify that the blend remains within quality parameters. Once homogenization is complete, the honey is transferred to the final holding tanks that feed directly into the packaging lines. These tanks are placed on load cells that precisely measure the volume of honey dispensed into each container. From this point forward, the product must move through sealed, temperature-controlled systems to ensure no contamination occurs before bottling. And that leads directly into the highly synchronized packaging phase. As the homogenized honey flows from the final holding tanks into the packaging system, the entire process becomes a high-speed, tightly orchestrated sequence of mechanical precision and hygiene control. This stage is where the product begins to take on its final consumer-facing form, whether it's packaged in squeeze bottles, glass jars, tubs, or bulk containers. The packaging line starts with the selection and preparation of containers, which are fed into the system from large hopper units or depalletizers, depending on the container type. Plastic bottles often arrive pre-formed and stacked in bulk, while glass jars may come in pallets wrapped in protective plastic film. Regardless of material, every container goes through a rigorous cleaning phase before it is allowed anywhere near the honey. The first step in container preparation is an air rinse or ionized air cleaning process. Each container is inverted and passed through a chamber where blasts of filtered, pressurized air are directed inside. Ionized air is used specifically to neutralize any static charges that might cause dust or particles to cling to the sides of the container. In glass packaging lines, this process may be supplemented with a vacuum extractor that removes dislodged particles immediately after the air rinse. Some facilities also opt for a UV light exposure chamber that the containers pass through as an added antimicrobial safeguard. All of these steps are executed on automated conveyor systems, synchronized to keep pace with the fill line. Now it's time to go into the filling stage, which must be executed with extreme accuracy to ensure every package contains the correct weight or volume of honey. Honey's thick, slow-moving consistency makes it a challenging product to fill efficiently at scale. To meet this challenge, factories use volumetric piston fillers or gear pump filling machines, both of which are well suited for handling viscous, sticky products. These machines are equipped with heated nozzles and jacketed tubing to maintain the honey at an optimal temperature, typically around 110 degrees Fahrenheit, so it flows smoothly without foaming or dribbling. Each filling station is designed with multiple nozzles, often ranging from 4 to 16, depending on the line's speed and scale. The nozzles are programmed to descend into the containers during filling and retract as the level rises, a method known as bottom-up filling. This minimizes splashing and helps prevent the introduction of air bubbles, which can interfere with the product's shelf stability and aesthetic appearance. Inline check weighers are stationed just downstream of the filling heads, automatically rejecting any underfilled or overfilled containers from the line. Any deviation outside a narrow tolerance window triggers an immediate alert and mechanical removal. Immediately after filling, the containers are transferred to the capping and sealing station. For plastic bottles, This often involves a torque-controlled capper that applies precise rotational force to ensure a tight but not damaging seal. Flip-top caps, disc-top caps, or screw caps are automatically sorted and fed into place using vibratory feeders and cap chutes. In the case of glass jars, the capping process may involve steam vacuum sealing with metal lids, creating a hermetic seal that ensures freshness and shelf stability. As the lid is applied, a puff of steam is injected into the headspace, which condenses and creates a partial vacuum as the jar cools. Some packaging lines also include an induction sealing station. This involves placing a foil liner inside the cap, which is then sealed to the lip of the container using electromagnetic induction to heat and bond the foil to the rim. This creates a tamper-evident barrier that reassures consumers while also acting as an additional contamination safeguard. Once sealed, the containers pass through a water or air rinse to remove any stray honey drips from the filling station, followed by a drying tunnel that uses forced warm air to eliminate surface moisture before labeling. But up next is the labeling and coding process, where the honey finally begins to take on its retail-ready appearance. Labeling machines apply product labels at high speed using pressure-sensitive or shrink-sleeve labels, depending on the packaging format. Pressure-sensitive labels are peeled from a backing roll and applied to the container with rollers, while shrink-sleeve labels are wrapped around the container and heat-shrunk into place using a steam tunnel. Each label is applied with extreme precision using optical sensors that detect the exact placement zone, ensuring uniformity across all units. At this point, the line integrates the critical traceability step, date coding, and batch identification. Inkjet or laser coders are installed directly after the labeling station and are configured to print the production date, batch number, and expiration date onto the label, cap, or bottleneck. These codes are essential for tracking product back to its source in the event of a recall or quality issue, and they also help with inventory rotation throughout the supply chain. Vision systems verify the presence and legibility of these codes, and any container missing its code is automatically rejected from the line. Once labeled and coded, the honey containers move toward the secondary packaging phase. Here, they are grouped based on retail configuration, single bottles, multi-packs, or cartons, and loaded into larger corrugated cardboard cases. Robotic case packers or drop pack mechanisms handle this process with extreme care, particularly with glass containers, which require dividers and cushioning. Once the cases are assembled and filled, they're sealed using hot melt glue or tape and then passed through a check weigher to verify package weight consistency. The final stage in the packaging process is palletization, where filled cases are stacked in precise formations onto wooden or plastic pallets. Robotic palletizers equipped with vacuum grippers or mechanical arms lift and arrange the cases row by row, ensuring that weight is evenly distributed to prevent collapse during transport. Once the pallet is complete, it is wrapped with industrial stretch film to stabilize the load and protect it from moisture and dust. Each pallet receives a barcode label containing all relevant shipping and traceability data, including product type, quantity, destination, and handling instructions. Now it's time to go into the warehousing and distribution stage, which is vital to maintaining honey's shelf life and ensuring that product quality is preserved from the factory to the consumer. Honey is hygroscopic, meaning it absorbs moisture from the air, so warehousing conditions must be carefully controlled. Finished pallets are moved to temperature and humidity-controlled warehouse zones where the ambient environment is kept between 60 and 75 degrees Fahrenheit, with relative humidity below 60% to prevent moisture ingress that could lead to fermentation or spoilage. Inventory is managed using a warehouse management system that assigns each pallet a digital location code, tracks product age, and ensures first in, first out rotation. automated guided vehicles or forklifts retrieve pallets based on shipping schedules, and every movement is recorded in a centralized database. This allows full traceability not just back to the packaging date, but all the way through, blending batches and raw honey origins. If a quality issue were ever discovered post-shipment, the manufacturer could instantly identify and recall only the affected lot numbers. Before pallets leave the facility, they may undergo one final inspection. Logistics personnel verify that labels match the shipping documentation, confirm temperature logs for any time-sensitive products, and ensure that stretch wrapping and labeling meet the receiving distributor's requirements. Some retailers have specific palletization rules, like maximum stack height or barcode placement, that must be followed exactly to avoid supply chain disruptions. Once cleared, pallets are loaded into temperature-controlled trucks using dock levelers that ensure a smooth transition from warehouse to vehicle. These trucks are often equipped with sensors that track internal temperature and humidity levels during transit. If any threshold is breached during transportation, alerts are sent to the distribution center to allow preventive action. This step is critical because improper handling during shipping can undo months of careful processing. For instance, exposure to excessive heat can darken the honey, degrade its enzymes, and even trigger fermentation if the moisture content is borderline. As the honey moves through regional distribution centers and into retail outlets, it remains in sealed containers that shield it from light and air. Most honey has a shelf life of 2 years or more if stored properly, thanks to its low water activity and high sugar concentration, which naturally inhibit microbial growth. However, the quality and freshness perceived by the consumer are still closely tied to how well every part of the manufacturing and distribution process has been executed, from the bee to the bottle to the shelf. Every detail, every degree of heat, every micron of filtration, and every second of line timing plays a role in preserving the integrity of the final product. And even after it reaches store shelves, the story of how honey is made in a factory continues to resonate with precision, craftsmanship, and scientific control. To fully understand the industrial production of honey, it's important to go beyond the mechanics and explore the subtleties of product customization, regulatory compliance, and the final quality control processes that make factory-scale honey not just uniform, but legally marketable and consumer safe. After the honey has been packaged, palletized, and staged for distribution, another dimension of the process becomes active: the post-packaging quality assurance system. This system acts as a final safeguard to confirm that the product leaving the facility not only meets internal quality standards, but also complies with local, national, and international food safety laws. One of the most essential tasks during this final phase is the detailed sampling and archiving of batch samples. From each production lot, designated containers are pulled from the finished goods and sent to the factory's on-site analytical laboratory. These samples are catalogued, sealed, and retained in climate-controlled archives for up to several years, depending on regulatory requirements. This ensures that if a complaint, audit, or issue ever arises, the facility can test the retained sample and compare it to the current product in question. The archive system is tied directly into the facility's digital traceability records, allowing a sample to be matched instantly to the exact floral source. Filtration parameters, blend ratios, packaging date, and even which employee signed off on the batch. Parallel to this, comprehensive chemical and microbiological testing is performed on the pulled samples. Even though honey is naturally resistant to microbial growth due to its low water activity and high sugar content, every lot is still tested for yeast, mold, and spore-forming bacteria, such as Clostridium botulinum. The latter is especially critical for honey intended for infant consumption. Though honey is generally not recommended for children under 1 year of age, Advanced polymerase chain reaction methods and microbial plating techniques are used in-house or sent to certified third-party labs for verification. The chemical testing regimen goes even deeper. In addition to previously mentioned standards such as moisture and HMF, tests are conducted to confirm that no contaminants have been introduced during packaging. This includes screenings for bisphenol A in plastic containers, phthalates, heavy metals like lead or arsenic, and residues from cleaning agents. Food-grade lubricants used in machinery are also tightly controlled to prevent incidental contact, and testing verifies their absence in finished products. Random bottles are sometimes subject to full shelf life simulation testing, where accelerated aging is used to project how the honey will behave under various conditions over time. Now it's time to go into the regulatory labeling and export compliance procedures, a crucial and often complex step for companies that ship honey across borders. Labeling is governed by a mixture of national food laws and international trade agreements. In the United States, for example, the Food and Drug Administration requires that honey be labeled with the common or usual name, net weight, ingredient list, the name and place of the business, and nutrition facts. Additional designations such as raw, organic, unfiltered, or wildflower must be substantiated with supply chain documentation and laboratory verification. For export to the European Union, labeling rules become even more intricate. The EU requires origin declarations if more than one country of origin is involved, meaning that a blend containing honey from, for example, Argentina and Canada must say, blend of honeys from more than one country, unless the exact percentages are broken down. Pollen analysis and isotopic testing are commonly used to verify the authenticity and origin of honey destined for the EU, and the entire production process must comply with the European Honey Directive. This includes ensuring that no heat treatment exceeds 40 degrees Celsius if the product is labeled as raw, and that no enzymatic activity is lost. The labeling department works in tandem with regulatory and export compliance officers, who maintain up-to-date databases of international standards, customs documentation, and product certifications. These certifications may include organic certificates, non-GMO verification, halal or kosher certification, fair trade documentation, and country-specific certifications of analysis. Every pallet destined for export is linked to a detailed manifest, and random audits ensure that the physical label matches its digital record in the product lifecycle database. Any discrepancy can halt a shipment and trigger a full traceability review. But up next is the specialization phase, where some facilities go beyond traditional honey and produce value-added variations to meet niche markets or changing consumer demands. This might include whipped or creamed honey, honey infused with natural flavors or botanical extracts, or honey blended with additives like royal jelly, bee pollen, or propolis. Each of these variations requires separate processing lines or batch scheduling to avoid cross-contamination and to comply with labeling laws that distinguish these products from standard filtered honey. Creamed honey, for example, requires controlled crystallization to achieve a smooth, spreadable texture. After filtration and homogenization, the honey is seeded with a small amount of finely crystallized honey and slowly stirred under cool temperatures in a creaming tank. This controlled environment allows microcrystals to form uniformly, resulting in a product that remains spreadable even when stored at room temperature. The tanks used in this process are jacketed with cooling fluid and fitted with slow-turning paddles that prevent the formation of large crystals. Flavored honey follows a different path. Natural flavor compounds, such as cinnamon, ginger, vanilla, lemon, or even chili, are emulsified into a small portion of honey before being slowly blended into the main batch. This ensures even distribution and prevents hotspots of flavor. Each additive must be food safe, approved by regulatory bodies, and tested for interaction with honey's enzymes and acidity. In some cases, additional filtration or viscosity adjustment is needed to maintain the same flow behavior in the bottling equipment. These specialty honeys are typically packaged in smaller volumes and targeted toward gourmet or health-conscious consumers.